For decades, the universe has sent countless visitors to our solar system, but none like 3I Atlas. This interstellar comet is carrying secrets from another star system, and it's making a brief close encounter with Mars. What does it hold? Why is its chemistry so unusual? And could it be delivering clues about life beyond Earth? Stay with us, because what 3I Atlas reveals could rewrite what we know about the cosmos. A quiet ripple in the scientific community often begins with data so subtle it looks like noise, yet in this case, two entirely separate announcements landed within the same cosmic window. NASA reported that Jezero crater on Mars revealed new textures in its layered mudstones, features that could be signs of biosignatures. At almost the same time, astronomers flagged an interstellar object, later named 3I Atlas, cutting across our solar system. The timing startled many. Was this mere happenstance or a glimpse into something far stranger? News of Jezero's leopard spots first reached headlines through a combination of high-resolution rover imaging and mineral analysis. The dark spots in light-toned sediments suggested unusual concentrations of iron sulfide and phosphate minerals. On Earth, such deposits often trace microbial activity in ancient riverbeds. Their sudden arrival in Mars' scientific narrative renewed public excitement over whether microbial life might once have flourished there. Almost in tandem, astronomers watching the sky for near-Earth objects spotted a fast-moving visitor whose trajectory proved unbound by the sun. Astronomers at ATLAS, a system built to catch asteroids that might strike Earth, announced the discovery with careful precision. The faint dot racing through their nightly survey data could easily have been mistaken for another faint comet. But precise measurements revealed its orbital eccentricity exceeded 1. That single mathematical value meant the object did not belong here. It was not looping back from a long orbit like familiar comets. It was cutting across the solar system on a one-time pass. The official designation, 3I Atlas, marked it as the third recognized interstellar object after Oumuamua and Borisov. The strangeness deepened because its trajectory intersected Mars's orbit in a way that almost felt scripted. While Oumuamua sped through without any planetary entanglement, and Borisov's path never brushed close to Mars, 3I Atlas seemed to aim itself toward a dramatic rendezvous. Planetary scientists called the geometry uncanny. As evidence of potential life was being weighed on Mars, a visitor from another star system approached for a near pass. Timing alone fanned the flames of speculation. Skeptics quickly pointed out that coincidences are inevitable in a universe filled with billions of stars and endless rocks drifting between them. Probability dictates that sometimes events align in ways that appear meaningful but are not. Yet within scientific communities, coincidence rarely remains a neutral word. Instead, it becomes a spark, a reason to test deeper connections. Was it possible that this visitor, rich in volatiles, carried clues about how life might emerge in planetary systems? Historical echoes only added weight to the moment. When Oumuamua passed, its tumbling cigar-like shape and lack of a visible coma launched debates about alien probes. When Borisov followed, its clear cometary tail calmed those theories but still raised questions about interstellar chemistry. Now, with 3I Atlas, the world faced a third act, this time coinciding with the search for Martian biosignatures. Each appearance built a narrative arc across years, tightening the web of speculation. The phrase cosmic coincidence surfaced repeatedly in headlines. Journalists played up the mystery, framing it as if the universe itself had staged a meeting between two stories: Mars' potential past life and the arrival of a messenger from afar. Scientists, more cautious, emphasized the need for careful observation. Still, the sense of drama was undeniable. The human mind resists randomness, preferring to stitch events into meaningful patterns. Philosophers of science often note that discovery thrives in moments of alignment. Darwin reading Malthus at just the right time, Einstein glimpsing the edge of Newtonian physics, such convergences fuel leaps forward. In planetary science, coincidences sometimes act as accelerants, focusing public funding and scientific curiosity on particular questions. Here, the overlap of Martian biosignature reports and 3I Atlas's approach did just that. An overlooked aspect of the coincidence lies in the technology involved. NASA's Perseverance rover, grinding through Jezero's delta, and the Atlas telescope scanning Earth's skies represent two extremes of observation. One probes the surface of a single planet in exquisite detail, while the other sweeps vast swaths of sky for faint moving specks. That both returned paradigm-shifting discoveries within weeks of each other demonstrated how interconnected our expanding toolkit of exploration has become. Meanwhile, speculation spread into realms less strictly scientific. Social media buzzed with questions. Could the interstellar object be deliberately aimed, a delivery of material to a planet on the verge of revelation? Some compared it to science fiction plots where alien civilizations time interventions with key evolutionary thresholds. Though no evidence supports such claims, the narrative gripped public imagination precisely because of the uncanny alignment. Scientists working with both datasets faced a dilemma. On one hand, caution demanded treating the two discoveries as unrelated. On the other, funding agencies and the public wanted links explored. Proposals began emerging for how Mars orbiters might look toward 3AI Atlas as it passed, hoping to intercept some of its dust. While not proof of connection, the coincidence encouraged imaginative leaps that could shape real observational campaigns. In academic circles, cosmic coincidence became shorthand for the event cluster. Papers submitted to planetary science journals noted the overlap, sometimes only in passing, but the phrase began to embed itself into the literature. Centuries from now, historians of science may look back on October 2024 as a moment when two parallel storylines converged, regardless of whether they truly connected. The coincidence also exposed something more human, our craving for meaning in a cold cosmos. Each data point, a mineral streak in Martian rock, a faint streak across a telescope's CCD, holds little by itself, but together, under the right timing, they feel charged. The idea that Mars might whisper of past life just as an emissary from another star streaked past struck chords too resonant to ignore. As scientists prepared for the flyby, the term cosmic coincidence moved from speculation to strategy. Agencies realized that public fascination could fuel budgets and attention. Outreach campaigns leaned into the mystery, promising to share updates on both Mars and 3i Atlas as they unfolded. Whether or not the universe had orchestrated the meeting, humans had decided to treat it as a story worth telling. And that is how coincidences transform into engines of discovery, not because they prove hidden forces at work, but because they mobilize attention, resources, and curiosity. October's overlap might have been nothing more than timing, but it set the stage for years of new questions about Mars, interstellar chemistry, and what it means to be watched by the universe itself. Was this truly only coincidence or the first hint that our universe arranges messages in plain sight? Stay with us as the mystery deepens. Leopard spots in the mud. The landscape of Jezero Crater has become the beating heart of Mars exploration, a natural laboratory where the layers of time remain locked in stone. Among the most startling discoveries made by Perseverance are irregular dark spots scattered across pale sediments, a feature scientists dubbed leopard spots. These strange markings are more than aesthetic. They may represent one of the strongest hints yet that Mars once supported microbial life. Close-up imaging by Perseverance revealed that the dark speckles follow mineral patterns rather than random scattering. Some of the spots appear concentrated where water once pooled, especially along the edges of ancient river channels that fanned into the crater. On Earth, such deposits often record microbial activity in deltaic environments. For geologists and astrobiologists, the realization was electrifying. Leopard spots might be a preserved chemical signature of biology long gone. Analytical instruments confirmed that the dark patches contained unusual concentrations of two key minerals, greigite, an iron sulfide ion, and vivianite, an iron phosphate. In Earth environments, both often form in association with microbial metabolic processes, particularly where oxygen is scarce but chemical energy abounds. The fact that Mars displays these minerals in contextual layers suggests that they may not be random geological products, but the residue of complex interactions between water, rock, and perhaps life. Equally compelling was the context. Jezero Crater was once filled by a lake fed by rivers that carried clays and sediments into its heart. The delta built there acted as a trap for organic molecules and minerals. On Earth, deltas are natural preservers of biosignatures, storing microbial mats, chemical gradients, and sediments that capture traces of organisms. The fact that leopard spots appeared specifically in this delta region heightened the likelihood that something extraordinary had been preserved. Another striking detail comes from Perseverance's SHE, RLOC, and PIXL instruments. which can analyse chemistry at fine scales. They revealed not just simple mineral presence, but gradients of iron and phosphorus in the spots. These gradients resemble those found in microbial colonies that concentrate elements for metabolism. If mere geology were at work, one would expect uniformity. Instead, Mars displayed heterogeneity that looked eerily biological. Skeptics, however, caution against overinterpretation. Minerals like greigite and vivianite can form through non-biological pathways, especially in water-rich environments with reducing conditions. Hydrothermal activity, chemical weathering, or mineral replacement could also produce the same signals. This tension between natural and biological explanations is central to Mars science. Each clue must be tested, each interpretation scrutinized before sweeping conclusions are drawn. The stakes rise because biosignatures on Mars would fundamentally alter our place in the cosmos. If leopard spots represent microbial activity, they would provide the first concrete evidence that life is not unique to Earth. Even if extinct, Martian microbes would demonstrate that biology emerges wherever water, chemistry, and energy converge. The implication would be staggering. Life could be the rule, not the exception, across the universe. Preservation of such signatures depends on mineral stability. Vivianite, for instance, forms only under reducing conditions with available phosphate. Once created, it can lock information about environmental chemistry for billions of years. That means the leopard spots could serve as microscopic time capsules, freezing the conditions of ancient Mars at the very moment life, if present, left its mark. One challenge lies in proving the biological case beyond doubt. For that, Mars sample return becomes critical. While rover instruments are powerful, laboratory tools on Earth can examine isotopes, organic molecules, and microscopic textures with far greater precision. Leopard spot samples, once delivered back to Earth, could be sliced into nanometer-thin layers, examined for microbial-like structures, and tested for fractionated isotopes that betray biology's hand. Another dimension comes from comparative planetology. Similar patterns of mineral deposition appear in Earth's own fossil-rich rocks, particularly in Precambrian sediments. Stromatolites, layered structures formed by microbial mats, often exhibit chemical zoning like that seen in Mars leopard spots. By comparing Martian and terrestrial examples, scientists can calibrate their expectations and refine their interpretations. Beyond the scientific community, the discovery of leopard spots captured public imagination. Media outlets latched onto the striking name, amplifying its mystery. The imagery, a barren Martian rock dotted with markings that resemble animal fur, made headlines accessible even to non-specialists. In outreach campaigns, NASA highlighted these spots as symbols of the tantalizing possibility that Mars's surface conceals hidden stories of life. The excitement also reignited debates within planetary ethics. If traces of life lie within Jezero's sediments, how should humanity approach them? Should they be preserved untouched, treated as sacred planetary heritage? Or should science pursue aggressive sampling, even if that means destroying tiny portions of potentially priceless fossils? Balancing curiosity with caution has become a recurring theme in Martian exploration. Future plans now revolve around how to prioritize these intriguing targets. Rover missions cannot collect unlimited samples, so scientists must choose wisely which cores to preserve for eventual return. Leopard spot-bearing rocks rank among the highest priorities. Their mineral chemistry makes them not just geologically interesting, but astrobiologically invaluable. A final, underappreciated aspect of the leopard spots is what they say about Mars's timeline. If indeed they formed through biological influence, it means life on Mars would have thrived during a window billions of years ago, when water still filled Jezero. That would place Martian biology contemporaneous with Earth's earliest microbes, suggesting life did not require exceptional circumstances, but arose naturally when the stage was set. The implications ripple outward. If Mars once hosted microbes, then interstellar objects like 3R Atlas carrying organic material become even more significant. Together, they hint at a cosmos where planets and drifting icy messengers might exchange ingredients for life. What looks like leopard fur on Martian stone could instead be the oldest testimony of biology's universality. Are these spot mere mineral quirks, or the fingerprints of Martian life itself waiting to be decoded? Come with us to explore the hidden corners of the story. The Night Watch. In the modern era of astronomy, humanity does not merely gaze at the stars in wonder, it keeps watch with machines that never sleep. Among the most vigilant of these guardians is ATLAS, short for the Asteroid Terrestrial Impact Last Alert System. Conceived as an early warning network for planetary defense, ATLAS spends every clear night scanning vast portions of the sky, searching for faint glimmers of movement that might betray incoming hazards. Ironically, while built to protect Earth from local dangers, ATLAS stumbled upon something far more exotic, an interstellar wanderer. The Atlas project began as a collaboration between NASA and the University of Hawaii's Institute for Astronomy. Its design goal was simple yet critical: detect small asteroids days or weeks before they could strike Earth. Unlike deep space telescopes that peer into narrow slices of the sky, ATLAS uses wide-field cameras mounted on modest telescopes, covering the entire visible dome multiple times per night. Its strength lies in breadth, not depth, scanning everything to catch anything. What makes Atlas remarkable is its vigilance. Each of its units, stationed at Mauna Loa and Haleakala in Hawaii, takes rapid exposures of the night sky. Advanced software compares images, flagging moving points of light that drift differently from stars. By repeating this process constantly, Atlas can detect objects as small as 100 meters with enough warning to prepare civil defense responses. In planetary protection circles, this system is viewed as humanity's night watchman. Atlas's contribution to science extends beyond asteroid defense. Its wide surveys generate immense catalogues of transient events: supernovae, variable stars, even comets. Astronomers across the globe often sift through ATLAS's alerts to chase phenomena unrelated to asteroids. In effect, ATLAS has become a multi-purpose sentinel, catching glimpses of the unpredictable sky in ways more specialized telescopes cannot. It was during such routine sweeps that 3i Atlas first appeared. A faint moving speck in the data stood out because of its unusual velocity. At first glance, the team assumed it might be another long-period comet. But within days, orbital calculations revealed a shocking truth: the object's eccentricity exceeded 1. This was no returning comet but an interstellar traveller cutting through the solar system. The system designed to warn us of danger had instead discovered a messenger from beyond. This was not the first time Atlas contributed to discoveries beyond its mandate. In previous years, it had spotted several near-Earth asteroids that passed surprisingly close, one of which skimmed Earth's atmosphere and created a fireball over the Caribbean. By catching them early, Atlas demonstrated its ability to serve as the planet's front line against cosmic intruders. That the same system now introduced the world to 3i Atlas only deepened its mystique. Atlas owes its success not only to its wide cameras, but also to clever software. Identifying a moving object in a sky filled with millions of stars requires algorithms capable of sorting faint signals from noise. Machine learning assists in this task, teaching the system to distinguish real asteroids from false detections caused by cosmic rays or sensor glitches. These automated filters ensure that Atlas spends its resources on genuine skywatching rather than chasing ghosts. The system's vigilance has sparked conversations about the philosophy of preparedness. For centuries, humanity was vulnerable to the whims of the cosmos, blind to incoming asteroids until they arrived. Atlas represents a shift, a deliberate decision to stop waiting for catastrophe and instead anticipate it. This watchfulness ties into a larger narrative: humans extending their senses outward, wrapping the planet in a protective shell of knowledge. Beyond Hawaii, expansion plans have placed ATLAS units in Chile and South Africa, creating a global network. By spacing the observatories around the Earth, scientists ensure near-continuous coverage, closing gaps caused by daylight or bad weather. This global distribution means no corner of the sky remains unmonitored for long. The interstellar discovery was thus not luck alone, but the natural outcome of a network built for resilience and reach. The discovery also underscores how instruments often transcend their original purpose. Atlas was never designed to uncover interstellar objects, yet its design principles, constant scanning, wide fields, and real-time analysis made it uniquely suited to catch them. This highlights a recurring truth in science. Sometimes the tools we build for one purpose inadvertently open entirely new frontiers. Atlas's watchful eyes also demonstrate the democratization of discovery. While giant flagship missions like Hubble or JWST dominate headlines, smaller systems like ATLAS quietly contribute breakthroughs. Its telescopes are not massive, its budget not vast, yet its role has proven indispensable. For students of astronomy, ATLAS serves as a lesson that discovery is not always about grandeur, but about persistence and clever design. The public perception of Atlas shifted dramatically after the 3i Atlas announcement. Suddenly, this quiet sentinel was thrust into the limelight as the system that spotted a visitor from another star. Media outlets highlighted its evocative name, dubbing it both Guardian of Earth and Discoverer of Aliens. Though scientists remained cautious in language, the symbolism was undeniable. Humanity's defense watchman had become a cosmic greeter as well. Some scientists argue that the 3i Atlas discovery could push governments to invest more heavily in similar systems. While planetary defense has long struggled for funding, attaching it to discoveries of exotic interstellar bodies provides a fresh incentive. If the same telescopes that protect Earth can also reveal cosmic wanderers, then their value extends beyond safety into the very heart of discovery. From another perspective, ATLAS embodies a deeper cultural moment. Humans are learning to treat the night sky not as a distant backdrop, but as an active domain requiring constant monitoring. Just as seafaring civilizations once stationed lighthouses along their coasts, we now station telescopes to warn of what approaches. That these watchtowers revealed an interstellar visitor gives the story an almost poetic resonance. In myth and folklore, watchers and sentinels often stumble upon unexpected arrivals, heroes, monsters, or messengers. Atlas's role fits this archetype perfectly. Tasked with protecting Earth from silent rocks, it instead announced the arrival of something far more mysterious. The Night Watchers fulfilled its duty, but in doing so it raised a new riddle. Why did this messenger arrive at this exact time? Could ATLAS's discovery be a fluke of surveillance, or is the cosmos trying to whisper something through its uninvited travellers? Let us guide you into what no one expected. What makes an object interstellar? Some objects in our solar system follow predictable orbits, looping around the Sun in paths that take them past planets and asteroids. But certain visitors are different. They appear to arrive from the vast darkness between stars. What sets them apart is their trajectory. Unlike planets, asteroids, or ordinary comets, which trace elliptical orbits with eccentricities less than 1, interstellar objects have hyperbolic trajectories. This means their eccentricity exceeds 1, a defining mathematical marker that signals an origin beyond the gravitational domain of the Sun. The eccentricity of an orbit measures its deviation from a perfect circle. For an interstellar object, an eccentricity greater than 1 indicates it is on an open path, never to return once it leaves the inner solar system. When astronomers first observed 3i Atlas, its calculated eccentricity soared well above 1, immediately setting off alarms. This was not just a comet with a curious tilt, it was a confirmed visitor on a one-way journey from another star system. Observers knew that whatever processes formed, it occurred in a distant environment, one that likely differs from the icy belts and nebula remnants we are familiar with. Velocity adds another layer of intrigue. Objects originating from the Oort cloud or Kuiper belt typically move at speeds consistent with the Sun's gravitational grip. In contrast, 3i Atlas was moving faster than what solar gravity alone would allow for a bound orbit. Its hyperbolic excess velocity, the speed above what would be needed to escape the Sun, was consistent with an origin outside our solar system. These measurements require precision. Astronomers must correct for observational parallax, Earth's motion, and even light pressure, making the detection of an interstellar trajectory an exercise in celestial exactness. One of the simplest ways to visualize why 3i Atlas is interstellar is to imagine throwing a ball on Earth. A typical baseball follows an arc and lands back on the ground. If you throw it fast enough to escape Earth's gravity, it leaves forever. In the cosmic scale, 3i Atlas is that ball, hurled into our solar neighbourhood from the void, passing close enough for telescopes to catch its fleeting presence. Unlike local comets, which are trapped in elliptical orbits and eventually return, 3i Atlas's path is one shot, a messenger from somewhere far away. The detection of interstellar objects is relatively recent. Before Oumuamua in 2017, astronomers had no confirmed evidence of objects arriving from other star systems. Its discovery shattered expectations, showing that our solar system is not a sealed environment, but an open crossroads where travellers occasionally wander. 3i Atlas continues that legacy, highlighting the small but but significant number of interstellar visitors that slip quietly past planets and telescopes, leaving hints in their wake. Gravitational interactions play a critical role in shaping hyperbolic paths. A comet entering the solar system may be deflected by Jupiter or Saturn, altering its trajectory slightly. For 3A Atlas, astronomers calculated that no such planetary encounters could account for its speed and angle. Its hyperbolic orbit remained intact, confirming that it was not an object previously captured by the Sun's gravity and later perturbed. This kind of orbital analysis requires careful modelling, integrating multiple years of potential positions and velocities, and simulating gravitational influences from every planet along the path. Beyond the numbers, there is the story told by dynamics. Interstellar objects act as time capsules from other systems. The direction from which they arrive hints at their stellar neighbourhood. While 3I Atlas's exact origin remains uncertain, astronomers can plot a probable inbound vector across the sky, correlating it with nearby stars and stellar associations. Even without visiting, these calculations allow scientists to hypothesize about the kind of planetary systems and formation environments that could have birthed this object. Observationally, interstellar objects challenge our infrastructure. They often appear unexpectedly and move rapidly across the sky, limiting the time for detailed study. Early identification is crucial. Ground-based survey telescopes like ATLAS are designed to detect fast-moving objects, providing initial positions and orbital data. Once flagged, follow-up observations from larger instruments refine the trajectory and confirm interstellar status. In 3I Atlas's case, the hyperbolic orbit was quickly confirmed by multiple teams, leaving no doubt about its outsider nature. The physical appearance of these objects adds another layer of curiosity. While an orbit tells us where it came from, a comet's coma and tail can offer hints about how it formed. Yet the first step is always understanding the orbit itself. 3I Atlas's path was its calling card, unmistakably different from comets native to the solar system. Hyperbolic, unbound, and moving faster than anything local, it signals a journey across light years, a traveller from a stellar nursery far from our Sun. Studying such trajectories also informs planetary defence. While interstellar comets pose no immediate threat due to their brief encounters, understanding their orbits refines our capacity to detect and track fast-moving objects in general. Techniques developed for hyperbolic visitors improve models for all cometary and asteroid paths, enhancing predictive power and situational awareness for any unexpected cosmic arrivals. Finally, confirming 3I Atlas as interstellar is not just an orbital victory but a philosophical one. Each hyperbolic visitor challenges assumptions about isolation and the uniqueness of the solar system. They remind us that stars exchange material, that planets and comets are not confined by stellar borders, and that even a small ice and dust bundle carries clues from across the galaxy. The very act of observing such a path redefines the boundaries of our celestial neighbourhood. Could this comet be the first of many interstellar messages passing through our solar system, each with a unique story to tell? Stay with us as the mystery deepens. Chemistry that doesn't fit. When astronomers first trained their spectrometers on 3A Atlas, the readings immediately raised eyebrows. Most comets in the inner solar system are dominated by water ice, with carbon dioxide and carbon monoxide present in smaller proportions. In contrast, 3I Atlas displayed a coma rich in carbon dioxide, and the ratio of CO2 to H2O was far higher than any familiar comet. This unusual chemical signature instantly suggested that it formed in an environment unlike our own, in a region where CO2 could condense and dominate volatile composition. The CO2:H2O ratio is more than a number. It tells a story of temperature, pressure, and chemical availability during formation. On Earth's comets, water ice forms closer to the Sun or in the cooler outskirts of the Kuiper Belt, while CO2 freezes at much lower temperatures, further from the warmth of the proto-Sun. Finding a comet where CO2 dominates implies it may have originated in a colder star system where the frost lines for these molecules differ. This ratio challenges our understanding of comet formation and forces scientists to revisit models of chemical condensation in protoplanetary disks. Early remote observations used infrared spectroscopy to identify volatile components in the coma. Infrared light interacts with molecular vibrations, producing telltale absorption features for CO2, H2O, CO, and other compounds. 3A's Atlas's spectrum showed unusually strong signals for CO2 at 4.3 microns, while water lines were comparatively weak. This signature is highly atypical for comets visiting the inner solar system, meaning that the body likely preserves chemistry from a distant, colder and more chemically isolated environment. Such findings are invaluable because they offer a glimpse of alien chemistry without leaving our solar neighbourhood. The dominance of CO2 also affects the comet's behaviour. CO2 sublimates at lower temperatures than water, meaning that 3I Atlas could develop a coma even when still far from the Sun. Observers noted that the comet began showing activity at distances where water ice would remain frozen solid. This early outgassing pattern hints at a surface layer or near-surface composition rich in carbon dioxide ice. The very way a comet interacts with sunlight can thus provide a chemical fingerprint, helping astronomers infer formation histories long before landing missions could ever arrive. Carbon dioxide also interacts with dust differently than water ice, influencing the visual appearance of the coma. As CO2 sublimates, it carries embedded grains outward, producing a more diffuse halo than water-dominated comets. For 3I Atlas, telescopes detected an extended, faint envelope surrounding the nucleus, indicating active sublimation at large distances. These observations allow scientists to model both the chemical and physical structure of the comet, revealing layers of ice and dust that may have remained pristine for millions of years. The unexpected chemical ratios also raise questions about stellar environment. In our solar system, water and CO2 compete for condensation in the protoplanetary disk. But in other systems, temperature gradients and stellar luminosity could invert those expectations. A CO2-rich comet suggests formation around a cooler star, or in a distant orbit around a Sun-like star, where carbon dioxide could freeze more readily. These chemical clues become a time machine, letting researchers peek into conditions that existed around another star, billions of kilometers away and millions of years ago. Interstellar exposure adds yet another layer of complexity. While in interstellar space, cosmic rays bombard the surface, altering molecular bonds and creating compounds that are uncommon in solar comets. CO2 might be preserved because it is more resistant to radiation than water, or because surface layers were shielded by dust. The precise ratios we observe today may therefore be a combination of primordial chemistry and billions of years of exposure to the harsh environment of interstellar space. This dual influence complicates but also enriches the story of its chemistry. Comparisons with other interstellar visitors highlight the anomaly. Borisov, the previous confirmed interstellar comet, showed a more balanced mix of water and CO2. Oumuamua, lacking a visible coma, offered almost no chemical signature but exhibited non-gravitational acceleration. 3I Atlas's chemical profile is unique not just among local comets, but even within the tiny sample of interstellar objects, indicating that the processes forming these bodies vary widely between star systems. Each visitor contributes a puzzle piece to the larger picture of galactic chemistry. Spectroscopic observations are not without challenges. Dust in the coma scatters light, background stars interfere with signals, and rapid rotation can produce transient changes in measured ratios. Despite these obstacles, multiple instruments on ground-based telescopes and space observatories independently confirmed the high CO2 content. The consistency across observations strengthens the argument that this composition is real, intrinsic, and not an artifact of measurement. It is a chemical signature waiting to be decoded. The implications extend beyond academic curiosity. CO2-rich comets could carry different organics, potentially including carbon-bearing compounds important to prebiotic chemistry. The unusual ratio suggests that materials forming in distant stellar systems may deliver a unique suite of molecules when visiting planets. While 3I Atlas itself poses no threat, understanding its chemistry could guide future planetary protection strategies and inform models for panspermia, the theory that life's building blocks may travel between stars. Every molecular measurement offers insight into alien systems. Observing the abundance of CO2 relative to water provides constraints on temperature, density, and chemical availability in its birth environment. Researchers can simulate the physical conditions needed to reproduce these ratios, allowing for theoretical models that point to CO2 ice lines, low temperatures, and reduced stellar irradiation. In essence, the chemistry transforms a passing comet into a laboratory for exoplanetary science, letting humans infer conditions millions of light years away. Might this unusual CO2 heavy makeup reveal completely new types of comets we never expected? Come with us to explore the hidden corners of the story. The Emerald Coma. The first images of 3i Atlas revealed an unexpected spectacle, a faint green glow surrounding its nucleus. Unlike the familiar icy or dusty halos of most comets, this emerald tint immediately drew attention. The colour itself is more than aesthetic, it signals specific chemical activity within the coma. In this case, the dominant contributors are thought to be diatomic carbon C2 and cyanide CN, molecules that fluoresce under solar ultraviolet radiation, producing characteristic green emission lines. Diatomic carbon is highly reactive and rarely observed outside cometary atmospheres. Its presence in the coma suggests that volatile carbon compounds are actively sublimating from the nucleus. When sunlight excites C2 molecules, they emit green light in a process called fluorescence, which creates the vibrant halo captured by telescopes. The intensity of this glow provides clues about the abundance of carbon-based volatiles and the comet's outgassing rate, turning what seems like a simple colour into a chemical diagnostic tool. Cyanide is another critical player in shaping the green hue. While its presence sounds alarming on Earth, in space, CN is a common product of organic and nitrogen-bearing molecules breaking down under sunlight. CN radicals emit in a spectral band near the green portion of the visible spectrum, complementing the emissions from diatomic carbon. Together, these molecules dominate the comet's coloration, offering an indirect window into its molecular inventory and suggesting that the object carries materials that are both volatile and chemically complex. The green glow also varies over time. As 3i Atlas approached the inner solar system, the intensity and spread of the coma changed in response to solar heating. Observations showed that portions of the halo brightened while others faded, hinting at localized activity on the comet's surface. This uneven outgassing may indicate a heterogeneous nucleus, with pockets of volatile-rich material emerging in bursts. In this sense, the emerald colour is a dynamic fingerprint, recording the comet's interaction with the Sun in real time. Analysing the coma's colour provides more than aesthetic delight. It enables chemical quantification. Astronomers can separate the green emission lines from the background continuum, allowing precise measurement of C2 and CN abundances. This information, when compared with models of cometary chemistry, can indicate the types of ices and organic compounds present within the nucleus. The unusual ratios observed in 3i Atlas suggest that these carbon compounds may have formed under conditions markedly different from those in our solar system. Ground-based telescopes were joined by space observatories to study the colour. Instruments on platforms like the Hubble Space Telescope and the James Webb Space Telescope captured high-resolution spectra, revealing subtle variations across the coma. These variations indicate complex chemical interactions between solar radiation, sublimated gases, and dust particles. Even minor changes in the coma's brightness or hue can reveal the presence of trace molecules, allowing astronomers to create a chemical map of this alien visitor. The interaction between molecules and sunlight also produces a subtle shift in wavelength known as the swings effect. For comets moving toward or away from the Sun, the Doppler effect alters the apparent position of emission lines, complicating spectral analysis. Observers of 3i Atlas carefully corrected for this, ensuring that the green light truly represented C2 and CN emissions rather than an artifact of motion. Such meticulous attention is necessary to confirm the chemical story hidden in the glowing halo. Colour can also hint at temperature and chemical pathways. Diatomic carbon is unstable at higher temperatures, so the prominence of green emissions suggests relatively low nucleus temperatures despite proximity to the Sun. The cyanide content indicates that nitrogen-bearing ices survive both formation and interstellar travel. Together, these observations allow researchers to infer environmental conditions both in the comet's place of origin and during its passage through space, turning a simple green halo into a multi-layered scientific narrative. Dust also influences the appearance of the coma. Tiny grains lifted off the surface scatter sunlight, softening and diffusing the emerald colour. Spectroscopy distinguishes between scattered light from dust and fluorescence from molecules, enabling accurate determination of volatile composition. The combined effect of chemical emissions and dust scattering produces a unique visual signature that identifies 3i Atlas among the multitude of comets observed in the solar system. Interestingly, the green glow is not permanent. As the comet recedes from the Sun, C2 and Cn molecules dissipate and the colour fades. This temporal evolution allows astronomers to track changes in outgassing and surface activity over time. By monitoring the hue's intensity and extent, scientists can model the sublimation of different ices and understand how interstellar comets respond to solar heating differently from native comets. The emerald coma also highlights the limitations of human perception. While the green light is subtle to the naked eye, sophisticated instruments can extract detailed chemical information. By combining imaging, spectroscopy, and time series analysis, researchers transform colour into a dataset, revealing not just what molecules are present, but their distribution, abundance, and evolution during the flyby. This makes the colour a bridge between visual observation and chemical insight. Comparing 3I Atlas with other green comets underscores its uniqueness. Most solar system comets show minor green emissions mixed with strong water-driven activity. 3I Atlas's combination of strong CO2 sublimation, a high C2 content, and an unusually prominent cyanide signature produces a particularly vibrant emerald hue. These differences reinforce the idea that interstellar visitors bring chemical compositions and behaviours not commonly seen in the local solar system, expanding our understanding of cosmic diversity. Finally, the green glow is a reminder of the unexpected richness of interstellar chemistry. What appears at first as a simple colour becomes a roadmap to formation environments, molecular survival, and interstellar history. It emphasises that even small comets are complex laboratories, capable of revealing conditions in distant systems without ever leaving our telescopes. The emerald halo is both a visual delight and a chemical message from beyond the stars. How will the emerald coma's subtle signals guide observations by orbiting telescopes and inform our understanding of alien chemistry? Let us guide you into what no one expected. Eyes in the Sky, JWST and SPHEREX. The journey to understanding 3I Atlas's unusual chemistry begins with its distant observers. From Earth, telescopes can capture only limited information, especially for fast-moving interstellar objects. Space-based observatories free from atmospheric interference offer a far clearer view. The James Webb Space Telescope, JWST, and SPHEREX emerged as key instruments for studying 3I Atlas, each bringing unique capabilities for identifying molecules in its coma and tail. JWST's infrared sensitivity is its greatest asset. Infrared light interacts with molecular vibrations, making it ideal for detecting CO2, H2O, CO, and organic compounds. For 3I Atlas, JWST could measure the specific wavelengths absorbed and emitted by these volatiles, revealing both their presence and relative abundance. Unlike ground-based telescopes, JWST operates above Earth's atmosphere, avoiding interference from water vapour that can obscure infrared signals. This allows for more precise identification of molecules that might otherwise remain hidden. SPHEREX, though designed primarily for all-ski spectral surveys, complements JWST by scanning a broad wavelength range and detecting chemical signatures across many targets simultaneously. While JWST focuses on high-resolution targeted measurements, SPHEREX can contextualize 3I Atlas among other comets, both interstellar and solar system natives. Its spectroscopic data provides a quick snapshot of the composition, allowing astronomers to verify JWST's detailed observations and identify any anomalies that warrant further scrutiny. Remote detection relies on a combination of spectral lines and continuum analysis. Molecules absorb light at characteristic frequencies and emit at others, creating a fingerprint unique to each species. In 3I Atlas, JWST captured clear emissions from CO2, while SPHEREX corroborated the presence of carbon-bearing compounds and detected minor contributions from Cn and C2. This cross-validation is crucial because remote observations are susceptible to noise, background light, and dust scattering, all of which can distort or mask signals. High spatial resolution is another advantage of space telescopes. JWST can resolve the inner coma, identifying regions of concentrated activity on the nucleus. By mapping chemical gradients across the comet's atmosphere, scientists can infer localized sublimation patterns, revealing which areas are rich in CO2, H2O, or organics. These maps are invaluable for understanding both the composition and the structure of the comet's surface, information that cannot be gleaned from Earth-based observations alone. Timing of observations is critical. Interstellar objects move rapidly across the sky, and their visibility windows are short. JWST and SPHEREX must coordinate schedules to capture the comet at moments when solar illumination maximizes emission lines, but before it moves too close to the Sun, where glare and thermal emission can hinder measurement. The precise orchestration of multiple observatories, both space and ground-based, represents a triumph of modern astronomy, turning fleeting opportunities into a lasting scientific record. Spectroscopic instruments themselves are sophisticated. JWST's NIR-SPEC and MIRI modules separate light into thousands of narrow wavelength bins, allowing scientists to detect even weak signals from minor molecular species. SPHEREX uses a low-resolution prism to survey large portions of the sky, identifying patterns that indicate unusual compositions. The combination of high-resolution detail and wide-area context provides a multi-layered understanding of 3I Atlas's chemical fingerprint. Interpreting this data requires careful calibration. Cosmic rays, thermal noise, and instrumental artifacts can mimic or obscure real spectral features. Teams working with JWST and SPHEREX must subtract these effects, often using reference stars or comparison regions of the sky. For 3I Atlas, such calibration was critical to confirming the dominance of CO2 over water and ensuring that the observed green emissions were real chemical signatures, not an artifact of observation. These telescopes also reveal physical dynamics alongside chemistry. By tracking how the coma evolves over days or weeks, astronomers observe variations in outgassing, which inform models of nucleus rotation, surface heterogeneity, and volatile layering. JWST can detect subtle differences in emission strength, while SPHEREX captures overall brightness trends. Together, they provide a temporal and chemical portrait of the comet as it journeys past Mars and out of the solar system. Beyond individual molecules, space-based spectrometers allow for detection of complex organics, including carbon chains and nitriles. These molecules fluoresce in specific infrared bands, and identifying them in 3I Atlas offers tantalizing hints about the comet's birthplace. Different stellar systems may produce different organic inventories, so measuring these compounds allows astronomers to start building a comparative chemical catalogue of interstellar visitors, a first step toward understanding galactic chemistry beyond our solar neighbourhood. Space telescopes also have the advantage of continuity. Unlike Earth-based instruments limited by daylight and weather, JWST and SPHEREX can monitor 3I Atlas continuously, providing data even during solar conjunctions when Earth-based observation is impossible. This uninterrupted coverage is essential for capturing peak outgassing events or sudden changes in coma chemistry, which could otherwise go unnoticed. Ultimately, these findings transform how we view interstellar visitors. Remote compositional measurements allow scientists to glimpse processes that took place billions of years ago across light years of space. The instruments do more than detect molecules, they link chemical signatures to the formation, history, and physical dynamics of distant systems. In this way, 3I Atlas is not just a transient visitor, it serves as a bridge to understanding planetary systems beyond our own, offering concrete data that informs models of exoplanetary formation and evolution. How will JWST and SPHEREX's observations illuminate the differences between 3I Atlas and its cosmic predecessors? And what secrets might the comet still reveal as it hurtles past Mars? Come with us to know. A Tale of Three Visitors. Interstellar objects are rare, but each one tells a distinct story about the cosmos. The arrival of 3I Atlas invites comparison with its predecessors, Oumuamua in 2017 and Borisov in 2019. While all three share the distinction of originating outside the solar system, their physical and chemical characteristics differ dramatically, offering unique windows into alien planetary systems and forcing astronomers to expand the catalogue of interstellar phenomena. Oumuamua was the first confirmed interstellar visitor, a cigar-shaped, highly elongated object with no detectable coma. Its strange trajectory, combined with unexplained acceleration, sparked both excitement and controversy. Unlike a typical comet, it appeared inactive, composed perhaps of dense rock or frozen volatiles that were not readily sublimating. This lack of a gaseous envelope set it apart from 3A Atlas, highlighting the diversity of objects traversing interstellar space. Borisov, in contrast, resembled a more familiar comet. It displayed a prominent tail and a water-dominated coma, behaving largely like comets from the Kuiper belt or Oort cloud. Its chemical signature included both H2O and CO, with CO2 present but not dominant. Borisov's activity and composition suggested formation in a protoplanetary disk similar to our own, making it a natural cousin of solar system comets despite its interstellar origin. It provided a direct comparison point for 3I Atlas and reinforced that interstellar visitors can present with a broad range of chemical signatures. 3I Atlas, however, combines features of both extremes. Like Borisov, it exhibits a bright coma, yet its chemistry is anomalous, with CO2 dominating and a striking green glow. Unlike Oumuamua, it is clearly active and releasing dust and gases as it nears the Sun. The differences among these three visitors reveal that interstellar objects are not a single category but a spectrum, each shaped by the conditions in its home system, the materials available during formation, and its long journey through the galaxy. The orbital characteristics of each visitor add another layer to the comparison. Oumuamua and 3's Atlas both followed highly hyperbolic paths, with eccentricities well above 1, confirming their extrasolar origins. Borisov's orbit was similarly hyperbolic, but its trajectory allowed for a longer observation window. Differences in approach vectors, speed, and timing provide clues about where each object came from and how gravitational interactions within their home systems shaped their ejection into interstellar space. Physical appearance also highlights the diversity of interstellar bodies. Oumuamua's elongated shape remains a subject of speculation, with models suggesting it could be a dense rock, a fractal aggregate, or even ice with unusual thermal properties. Borisov was more rounded, with a recognizable nucleus and extended tail, aligning with the expectations for solar system comets. 3I Atlas introduces a new visual element, the emerald coma, linking chemical composition directly to observable color and activity, an aspect not evident in either Oumuamua or Borisov. Chemical behavior provides further contrast. Oumuamua lacked detectable volatiles, though non-gravitational acceleration hinted at possible outgassing. Borisov followed classical cometary behavior, with water sublimation driving its tail. 3I Atlas, by contrast, shows a CO2-rich outgassing profile and unusual C2/CN ratios, revealing that interstellar objects can form in environments markedly different from our solar system. Each body thus expands the chemical palette astronomers must consider when studying alien comets. Observation strategies have evolved alongside these discoveries. Oumuamua required rapid identification and continuous monitoring to track its fast-moving path. Borisov's more prominent activity allowed longer-term study, including spectroscopy to probe composition. 3I Atlas combines the challenges of speed, chemical complexity, and solar proximity, necessitating the use of both ground-based and space-based instruments to capture its full chemical and physical story. This progression underscores how interstellar studies rely on flexible and multifaceted observational approaches. The lessons extend to planetary science. Each visitor provides a natural sample of material formed elsewhere in the galaxy, enabling indirect studies of other planetary systems. Oumuamua's rocky or icy nature, Borisov's water-rich composition, and 3I Atlas's CO2 dominance offer complementary datasets. Together, they suggest that planetary formation is not uniform, that chemical diversity is the rule rather than the exception, and that interstellar objects are messengers carrying clues to processes otherwise inaccessible to observation. The story of these visitors also reveals limitations in interpretation. Sparse observations, rapid motion, and environmental effects like solar radiation or cosmic rays can alter appearance and activity. Oumuamua's acceleration, initially mysterious, might be explained by subtle outgassing undetectable at the time. 3I Atlas's colour and chemical ratios, while distinct, may evolve as it passes perihelion. Comparing objects highlights how much depends on observation timing and instrument sensitivity, and how apparent anomalies can often be understood through natural mechanisms. observations of this trio emphasize the broader cosmic perspective. Interstellar visitors reveal that our solar system acts as a crossroads, where objects from far-off star systems occasionally traverse, bringing distinctive chemical and physical traits. They push astronomers to sharpen models of planetary formation, chemical variety, and interstellar motion. Every new arrival adds a piece to the mosaic of galactic processes, proving that even brief visitors can shed light on profound truths about the universe. What hidden details will emerge when 3i Atlas is analysed alongside its predecessors, and how might these interstellar comparisons reshape our understanding of chemical diversity across the galaxy? Walk with us into the truth that was never meant to surface. Orbital geometry and dramatic timing. The path of 3 Atlas through the solar system reads like a carefully choreographed cosmic ballet. Its orbit is not only hyperbolic, but also angled in a way that creates a brief, almost cinematic encounter with Mars. The combination of perihelion distance, inclination, and the timing of its approach makes this flyby both scientifically valuable and visually striking. Understanding the orbital geometry is key to appreciating why the encounter appears both close and elusive from Earth. The comet's perihelion, the point in its orbit closest to the Sun, is unusually positioned relative to both Earth and Mars. As it swoops inward, 3i Atlas passes on a trajectory that places it near Mars, yet largely out of view from terrestrial observatories. The alignment of Earth, Mars and the comet means that while Mars orbiters have a near-perfect vantage point, ground-based telescopes face the glare of the Sun. This geometric coincidence is rare, providing a natural laboratory for observing interstellar material from multiple angles simultaneously. Inclination further shapes the encounter. 3i Atlas approaches the solar system from a steep angle relative to the ecliptic plane, the flat disk in which most planets orbit. This high-inclination orbit limits interactions with other planets and reduces gravitational perturbations, helping maintain its hyperbolic trajectory. For observers, it also means the comet crosses the sky quickly, changing position dramatically over a matter of days. Tracking this motion requires rapid response observation strategies, precise calculations, and coordination between instruments in orbit and on the ground. Timing amplifies the drama. The comet's perihelion occurs near a window when Mars is ideally placed for observation, but Earth is not. This solar conjunction blackout, when the Sun sits between Earth and the comet, creates a brief period in which terrestrial observation is severely limited. Instruments in Mars' orbit become crucial, capable of capturing data that would otherwise be impossible. This intersection of orbital geometry and timing transforms a routine flyby into a cinematic event, reminiscent of the rare alignments that shape eclipses or planetary transits. Hyperbolic velocity plays a role in both opportunity and challenge. Travelling faster than escape speed from the Sun, 3i Atlas zips past planets in a matter of weeks, leaving narrow windows for measurement. The speed also amplifies gravitational deflection from nearby planets, requiring precise calculations to ensure that predicted positions match observed locations. The comet's rapid transit means that instruments must act quickly, capturing high-resolution imagery and spectroscopy before it disappears into interstellar space again. The comet's path relative to the Sun also affects illumination and observed chemistry. As 3i Atlas approaches perihelion, the Sun heats its surface, driving sublimation of volatiles and increasing coma brightness. From Mars' orbit, the Sun illuminates the comet at an optimal angle, highlighting chemical emissions and enhancing spectral signals. Observers can measure CO2, CN, and C2 more effectively than from Earth, taking advantage of a naturally favourable geometry that accentuates subtle features in the coma and tail. Gravitational interactions, though minimal, also factor into timing. Mars, though small compared to Jupiter, exerts a slight influence on the comet's trajectory. Calculations show that 3i Atlas's path would remain hyperbolic even without this planetary nudge, but the close approach introduces a small deflection that slightly changes predicted positions. Accounting for such influences is crucial for orbit refinement and ensures that space-based instruments can point accurately to capture high-quality data during the fleeting encounter. Projection against the starfield adds another layer of observational challenge. From Earth, the comet moves against a crowded backdrop of stars, its motion creating streaks in long exposures. From Mars' orbit, the motion is slower relative to the background, allowing sharper images and cleaner spectral measurements. This geometric advantage underscores why orbital perspective can be just as important as instrument capability in obtaining meaningful scientific data from a transient interstellar visitor. The combination of approach angle, velocity, and distance also affects the comet's apparent size and brightness. At closest approach, 3I Atlas will appear relatively small but sufficiently luminous for sensitive instruments to resolve detailed structure in the coma. Observers can track changes in emission intensity across the surface, detect variations in dust production, and monitor fluctuations in chemical ratios. The geometry of the encounter maximizes the observable signal despite the comet's vast distance. Orbital geometry ultimately highlights the delicate dance between chance and cosmic mechanics. A small change in the comet's ejection speed from its home system could have sent it on a path that either missed Mars completely or provide an even better viewing angle from Earth. The current trajectory represents a near-perfect alignment of velocity, inclination, and planetary positioning, allowing astronomers to study interstellar chemistry and dynamics in ways that would otherwise be impossible. How will the carefully choreographed geometry of 3I Atlas influence observations of its outgassing patterns and chemical profile, and what hidden details might the alignment reveal about its interstellar origin? Stay here as the next twist unfolds. Mars orbiters on the watch. The October flyby of Oumuamua. Atlas presents a rare opportunity for Mars orbiters to act as frontline observers of an interstellar visitor. Instruments aboard spacecraft like Mars Express, the Trace Gas Orbiter, TGO, and MAVEN can monitor both the physical structure and chemical composition of the comet in unprecedented detail. Unlike Earth-based telescopes, these orbiters operate without atmospheric interference, providing a direct line of sight to the comet's coma and tail as it passes millions of kilometers away. Mars Express, one of the oldest orbiters still active, carries imaging spectrometers and high-resolution cameras capable of detecting faint variations in coma brightness. The orbiter's HRSC camera can track outgassing plumes and dust jets, mapping them relative to the nucleus over time. Even small features, tiny eruptions of CO2 or localized dust bursts, become detectable, allowing scientists to correlate activity with rotation and solar illumination. The precise temporal tracking provides a dynamic view of how the comet evolves during its rapid passage. The Trace Gas Orbiter adds a complementary perspective with its suite of spectrometers. TGO can detect infrared emissions from volatile molecules, enabling detailed measurement of CO2, H2O, and minor organics such as CN and C2. These observations help quantify the abundance ratios in the coma, which is critical for understanding the comet's origin and internal structure. The orbiter's orbit around Mars provides multiple viewing angles, which allow scientists to model the three-dimensional distribution of gases as the comet sweeps past. MAVEN, designed to study Mars' upper atmosphere, offers an unexpected advantage for this mission. Its instruments can detect high-energy particles and the interaction between the comet's outgassing and the solar wind. As CO2 and other volatiles leave the nucleus, they may ionize under solar radiation, creating charged particle streams. MAVEN's particle detectors can capture these events, revealing subtle interactions that provide clues about the comet's activity and the way interstellar materials respond to solar radiation. Observation timing is crucial for all orbiters. 3I Atlas moves rapidly, limiting windows when instruments can collect data without motion blur or exposure saturation. Coordinating the instruments requires meticulous planning, accounting for orbital passes, line-of-sight alignment, and sunlight angles. Scientists must schedule imaging and spectroscopy in narrow windows, often lasting only hours, to ensure that each orbiter captures complementary data sets. The interplay of speed and distance makes these observations both challenging and valuable. Each orbiter brings unique sensitivities to specific wavelengths. Mars Express excels at visual and near-infrared imaging, TGO specializes in mid-infrared detection of molecular emissions, and MAVEN monitors energetic particles. Combining these data allows for a comprehensive chemical and physical profile of the comet. This multi-instrument approach also mitigates potential observational biases, ensuring that any anomaly detected is a real feature rather than an artifact of a single instrument. Dust detection is another focus. Orbiters can track how dust grains are released from the nucleus and form the extended tail. High-resolution cameras and particle detectors capture size distribution, density and motion of dust particles. These observations reveal the surface heterogeneity of the comet and provide indirect insights into its internal layering. Differences in particle size may indicate regions rich in CO2, ice versus H2O ice or organic compounds, helping to reconstruct its formation environment. The orbiters also allow for repeated observations, capturing the evolution of the outgassing over days. As 3I Atlas approaches and recedes from perihelion, the composition of the coma can shift, revealing layers that were previously shielded. Mars orbiters can track changes in emission line intensity and tail morphology, helping scientists understand selective sublimation processes and the comet's internal structure. Such time-resolved data is critical for interpreting the unusual CO2:H2O ratios that distinguish this interstellar visitor. In addition to chemistry, orbiters can provide positional verification for orbital models. 3I Atlas follows a highly hyperbolic trajectory, and slight perturbations from solar gravity or interactions with solar wind can subtly shift its path. Precise imaging and astrometry from Mars orbiters refine calculations of its orbit, improving future predictions and helping to validate models of interstellar object dynamics. Even minor adjustments in predicted position can impact the interpretation of spectral data, highlighting the importance of accurate tracking. The flyby also tests the limits of instrument capabilities. Measuring faint molecular emissions across tens of millions of kilometers requires extreme sensitivity and calibration. Temperature fluctuations, stray light from the sun, and interference from Martian atmospheric scattering all pose challenges. Teams must carefully correct for these factors to ensure that detected signals accurately represent the comet's outgassing and dust emissions. The success of these observations demonstrates the versatility and endurance of Mars orbiters decades after their initial deployment. Each spacecraft contributes a complementary perspective that Earth-based telescopes cannot provide. While ground observatories can sometimes capture spectral snapshots, the orbiters enjoy uninterrupted coverage during solar conjunction when Earth's view is blocked. This allows continuous monitoring of rapid changes in the coma and tail. By combining visual, infrared, and particle data, the scientists build a multi-dimensional picture of the comet, capturing both its physical dynamics and chemical evolution in real time. Beyond immediate science, these observations offer a rehearsal for future interstellar encounters. Techniques honed for tracking and analyzing 3I Atlas will inform strategies for potential sample return missions or targeted flybys. Understanding how orbiters detect volatile ratios, dust properties, and ionized particles provides a blueprint for extracting maximum information from objects traveling at extreme speeds and across vast distances. These lessons will be critical if humanity ever attempts direct interaction with interstellar material. The orbiter's contributions extend to public engagement as well. By sharing data and imagery in near real time, missions like Mars Express and TGO bring distant interstellar phenomena into accessible view. The combination of high-resolution images, colourful emission maps, and chemical data creates a narrative that captures both scientific and popular imagination. Observing the comet through the eyes of orbiters highlights the interplay of technology, geometry, and cosmic timing, turning abstract science into tangible discovery. What unexpected features might Mars orbiters reveal in the dust, gases, or transient activity of 3I Atlas? And how will these findings challenge our understanding of interstellar visitors? Let us tell you. A thought experiment. Imagining the use of a 3I Atlas for terraforming. Mars stretches the mind beyond conventional exploration. The comet carries an inventory of volatiles, organics, and dust, elements that could theoretically influence a planetary atmosphere if delivered in sufficient quantities. While the scale of a single interstellar visitor is far too small to alter a planet meaningfully, considering its chemical cargo provides insight into the priorities for any future large-scale planetary engineering effort. CO2 dominates 3I Atlas's outgassing profile, a fact that immediately captures attention in the context of terraforming. On Mars, CO2 is already present in polar ice caps and the thin atmosphere, but it is insufficient to raise surface pressure or temperature significantly. A comet like 3I Atlas could, in theory, supplement Mars' CO2 inventory, temporarily thickening the atmosphere and contributing to greenhouse warming. While the effect of one comet is negligible, the exercise clarifies which volatiles are most critical to planetary modification. Water is another essential component. 3I Atlas displays a lower H2O proportion than CO2, emphasizing the importance of scaling delivery. For any terraforming scenario, water is vital for both climate moderation and potential biological introduction. Observing how 3I Atlas releases H2O as it nears the Sun provides a natural experiment in sublimation dynamics, offering a model for controlled delivery of ice or vapor to a planetary surface. Understanding these sublimation rates informs engineering strategies for future missions. Organics add an additional layer of intrigue. Interstellar comets may carry simple carbon chains, nitriles, and complex molecules that could seed prebiotic chemistry on Mars. Even trace quantities can serve as chemical markers, helping to study how exogenous organics interact with Martian regolith and atmospheric gases. While a single flyby cannot initiate life, it serves as a thought experiment. How would humanity prioritize organics if the goal were to catalyze chemical evolution on another planet? Dust particles from the comet also play a conceptual role. Fine grains can transport minerals, trace elements, and additional volatiles. In a terraforming scenario, dust deposition could help fertilize the surface or contribute to cloud formation, influencing climate. Observing how 3I Atlas's dust interacts with solar radiation and the Martian environment offers insights into particle behavior under low-pressure, high radiation conditions, which is essential for understanding delivery mechanisms. The dynamics of the comet's trajectory provide further lessons. 3I Atlas is moving at tens of kilometers per second, making physical interception impractical with current propulsion technology. Any real terraforming application would require slower, controlled delivery systems, emphasizing the importance of trajectory planning and orbital mechanics. The comet's hyperbolic path highlights the difference between naturally occurring flybys and engineered interventions. Thermal processing of cometary material also merits attention. As 3I Atlas approaches perihelion, heating drives sublimation and exposes inner layers, releasing trapped volatiles and organics. This natural laboratory allows scientists to study which compounds are more resistant to radiation or thermal stress. For terraforming, understanding which materials survive transit, release timing, and chemical integrity can guide choices in artificial delivery methods, such as deploying ice-rich payloads into planetary orbit. Selective sublimation has implications beyond chemistry. 3I Atlas's surface is likely layered, with CO2-rich crusts concealing water ice and other volatiles beneath. Observing how heating exposes inner layers informs predictions about resource accessibility. If humans ever attempted large-scale delivery of cometary material, knowing which layers sublimate first and which remain insulated would be critical for efficient utilization of resources. The chemical composition itself provides clues about extraterrestrial environments. CO2 dominance suggests formation near a freeze line in another planetary system, while the presence of complex organics indicates available carbon-rich material. For terraforming considerations, this helps identify which comets or asteroids might offer the richest mix of greenhouse gases and organics, guiding hypothetical resource selection in a forward-looking planetary engineering scenario. Atmospheric interaction on Mars is another consideration. If 3I Atlas's volatiles could be delivered in bulk, they would interact with existing CO2, dust and trace gases, potentially producing short-lived weather phenomena. Even without terraforming, studying the deposition and dispersal of cometary gases during a flyby provides valuable data about gas dynamics, chemical reactions under Martian conditions, and the stability of volatile compounds in a thin atmosphere. Risk assessment is integral to the thought experiment. Cometary delivery introduces unknown factors. Reactive organics, dust, and trace heavy metals could produce unexpected chemical reactions. While 3I Atlas presents no real threat during its natural flyby, imagining the deliberate use of such material underscores the importance of understanding chemical stability, sublimation behavior, and interaction with planetary surfaces before any large-scale intervention is considered. The thought experiment also encourages consideration of cumulative effects. One small comet cannot terraform a planet, but multiple deliveries over centuries could, in theory, accumulate sufficient greenhouse gases and water to modify the environment incrementally. Observing 3I Atlas's contribution highlights both the limitations of single encounters and the principles of additive interventions, providing a framework for evaluating long-term planetary engineering strategies. Beyond raw materials, observation of 3I Atlas informs technology development. Sensors on Mars orbiters detecting CO2, water and organics offer a template for designing payloads capable of remotely analysing future delivered material. Techniques refined during this flyby can guide the creation of instruments for sample return missions, resource assessment, and monitoring the distribution of volatiles on planetary surfaces. Ultimately, this thought experiment brings ethical considerations into focus. Even in a hypothetical terraforming scenario, humanity must weigh the consequences of introducing extraterrestrial material. While 3I Atlas is naturally transient, deliberate intervention raises concerns about contamination, planetary protection, and balancing scientific curiosity with environmental responsibility. Studying its composition and behaviour highlights the importance of caution and informed decision-making. What volatiles and organics would be most valuable if humanity could engineer delivery to Mars? And how does observing 3I Atlas refine our understanding of which resources are truly critical? Stay with us to see what lies ahead. Natural birthplaces. Every comet carries a story about the environment in which it formed, and 3I Atlas is no exception. Its CO2-dominated composition immediately suggests a birthplace near the CO2 ice line of its parent system. In protoplanetary disks, different volatiles condense at specific distances from the central star, forming distinct zones where water, carbon dioxide and other molecules freeze. Observing 3I Atlas provides a rare window into these alien chemical neighbourhoods. The CO2 ice line is further from a star than the water ice line, existing where temperatures are low enough for CO2 to freeze solid. Comets forming near this line can incorporate abundant carbon dioxide while water ice remains limited, explaining the unusual CO2:H2O ratios seen in 3I Atlas. This contrasts sharply with solar system comets, which typically form closer to the water ice line and show water-rich compositions, emphasizing the diversity of planetary system chemistry across the galaxy. Disk dynamics influence where comets accumulate volatiles. Gas pressure, turbulence, and the radial flow of material can concentrate certain ices in specific regions, creating layered structures in cometary nuclei. 3I Atlas's CO2-rich outer layer may reflect these processes, while water and organics remain buried beneath, insulated from early sublimation. Understanding these structures helps model how protoplanetary disks sort materials during planetary formation. The influence of stellar type is critical. Stars of different masses and luminosities have ice lines at varying distances, meaning a CO2-dominated comet could form relatively closer to a dim star, or much farther from a bright star. 3I Atlas's composition may hint at the type of stellar nursery it emerged from, offering clues about temperature gradients, disk chemistry, and the potential for habitable zones in that system. The CO2 dominance is not random but a signature of its natal environment. Migration within the disk can further modify compositions. Interactions with forming planets, disk instabilities, or stellar radiation can move small bodies inward or outward, altering exposure to heat and irradiation. 3I Atlas may have undergone such migrations, acquiring its unique volatile mix while avoiding destructive heating that would sublimate key compounds. Observing how these elements are distributed in the coma informs models of early dynamical histories in alien systems. Comparing 3I Atlas with solar system comets reinforces the significance of its birthplace. While most comets near Earth originate in regions where water ice is abundant, 3I Atlas's CO2 dominance challenges assumptions about uniform formation conditions. It demonstrates that even though minor changes in disk temperature or chemistry can produce bodies with radically different chemical profiles. Each interstellar visitor thus expands our understanding of planetary system diversity. Laboratory simulations support these interpretations. Experiments replicating low-temperature condensation in protoplanetary disk analogues show that CO2 condenses into solid ice beyond certain distances, while water remains gaseous or forms thinner layers. These models align with the observed composition of 3I Atlas, validating the hypothesis that its outer layers formed near a CO2 ice line. Observing natural analogues in situ strengthens the connection between theory and cosmic reality. Isotopic ratios may offer additional evidence for its birthplace. CO2 and water carry distinct isotopic signatures depending on formation temperature, solar radiation exposure, and chemical environment. Measuring these ratios remotely via spectroscopy provides a method for confirming the comet's origin zone without needing a sample return. Early observations of 3I Atlas indicate ratios consistent with a cold CO2-rich environment supporting the ice line hypothesis. The comet's hyperbolic trajectory implies it was ejected from its home system, likely by planetary scattering or dynamical instability. Ejection preserves the original compositional signature, meaning 3I Atlas is essentially a frozen chemical snapshot from another star system. This preserved material is invaluable for testing models of disk chemistry, volatile distribution, and planetesimal formation under conditions vastly different from our own solar system. Thermal evolution during its journey adds complexity. While interstellar exposure gradually alters surface chemistry, the CO2 layer may have acted as a protective shield, preserving inner water ice and organics. Observing current outgassing patterns gives scientists clues about what is primordial versus modified, offering insight into how comets maintain or lose chemical integrity over millions of years of interstellar travel. 3I Atlas becomes a time capsule, bridging the past and present of its formation environment. Modelling CO2 ice line formation also provides context for exoplanetary studies. Planets forming within these disks may inherit atmospheres enriched in CO2 or other volatiles shaping habitability and climate. 3I Atlas acts as a natural probe, allowing scientists to test theoretical predictions about chemical gradients, volatile migration, and ice accumulation in alien planetary systems. Its flyby turns abstract modelling into observable reality. The physical layering of 3I Atlas reinforces the ice line scenario. If CO2 condensed on the surface while water remained buried, early sublimation would produce the skewed ratios now observed. As perihelion heating exposes deeper layers, we might expect water emissions to increase relative to CO2. This dynamic behaviour mirrors the expected structure of ice line-formed comets, offering a live demonstration of protoplanetary disk processes in action. Solar system comparisons continue to be instructive. Whereas Oumuamua lacked a detectable coma and Borisov had water-dominated emissions, 3I Atlas exemplifies the chemical diversity that results from formation location within a disk. The CO2 ice line hypothesis not only explains its composition, but also provides a framework for understanding the spectrum of interstellar objects we may encounter in the future. Each new visitor expands the map of chemical possibilities. The comet's passage past Mars offers a final observational advantage. Instruments capable of measuring volatile ratios and dust particle composition can directly test the CO2 ice line hypothesis. Observing which layers sublimate first, the relative abundance of CO2 to water, and the presence of minor organics allows scientists to reconstruct the early environment of its home system. The flyby becomes a direct probe of exoplanetary disk physics. How did the CO2 ice line shape theory? 3I Atlas's chemistry and structure, and what secrets about alien planetary disks lie hidden beneath its frozen exterior? Stay with us to uncover the truth. Selective sublimation, layers that lie. The outgassing of 3I Atlas reveals a subtle but crucial principle of cometary physics. Not all layers release their volatiles evenly. The outer crust of a comet often differs drastically in composition from the inner layers, leading to selective sublimation. For 3I Atlas, as you see, the dominance of CO2 in the coma indicates that its surface is coated with CO2-rich ice, while water and other volatiles remain insulated beneath, masked from early observations. Surface insulation can result from dust accumulation and volatile depletion during past interstellar travel. Cosmic rays slowly alter exposed material, creating a refractory layer that traps underlying ices. This layer delays sublimation of water and organics, meaning early observations capture an incomplete picture of the comet's chemistry. Only as 3I Atlas approaches the Sun does solar heating penetrate deeper, revealing previously hidden material in the nucleus. Layering is not uniform. Localized jets may erupt where fractures or weak points expose inner ices, creating a heterogeneous coma. This patchy sublimation produces transient spikes in certain molecular emissions, complicating chemical analysis. Observing these patterns from Mars orbit allows scientists to map activity across the nucleus and understand which areas are CO2 rich, which harbour water ice, and where organics are likely concentrated. Thermal conductivity plays a key role in selective sublimation. CO2 sublimates at lower temperatures than water ice, meaning the outer crust reacts first to solar heating. Water remains trapped beneath until the heat wave penetrates deeper. This delay produces an initially skewed CO2:H2O ratio in the coma, explaining the unusual chemical profile of 3I Atlas and demonstrating the importance of considering layered structure when interpreting remote observations. The thickness of the CO2 crust can vary with nucleus morphology. Flattened or concave surfaces may retain volatiles longer due to reduced solar exposure, while ridges and exposed edges heat more efficiently. Such topographical variations influence local sublimation rates, creating a dynamic and evolving coma. By monitoring changes in emission patterns, scientists can infer the geometry and orientation of the comet's surface layers. Cosmic ray processing complicates matters further. Prolonged exposure in interstellar space can chemically alter outer layers, producing a hardened, carbon-rich crust that masks underlying ices. These alterations may modify the volatile ratios measured remotely, creating the appearance of a chemically unusual comet. Understanding the effect of interstellar processing is essential to distinguish primordial chemistry from surface evolution. The interplay of thermal gradients and material composition explains episodic activity. Jets of CO2 may erupt sporadically when weak spots are exposed, while water and organics remain trapped until deeper heating occurs. This selective sublimation highlights the importance of timing in observations. Measurements taken too early may underestimate water content, while those after perihelion may reveal previously hidden components, changing interpretations of formation conditions. Observations of 3I Atlas provide natural confirmation of these theories. High-resolution imaging shows varying brightness in different coma regions, correlating with molecular emission patterns. Spectroscopic measurements detect CO2 consistently early in the flyby, while H2O lines intensify closer to perihelion, illustrating the layered nature of the nucleus. These observations serve as a live laboratory for understanding selective sublimation dynamics in interstellar objects. Comparing 3I Atlas with solar system comets reinforces these concepts. While water-dominated comets often show immediate H2O emission upon solar approach, interstellar visitors like 3I Atlas may carry surface layers significantly enriched in CO2. This difference highlights the diversity of formation conditions and the importance of surface processing. Each comet teaches a unique lesson about the interplay between primordial composition and subsequent evolutionary history. Dust plays a complementary role in selective sublimation. Fine particulate material on the surface can insulate ices, delaying sublimation or channeling jets through fractures. Dust grains can carry organics and trace minerals, contributing to the observed coma composition. Observing how dust interacts with outgassing provides insight into the mechanical and thermal properties of the nucleus, offering indirect evidence of subsurface layering. Thermal models of sublimation predict the timing and sequence of volatile release. For 3I Atlas, CO2 emerges first, followed by water and minor organics, consistent with observations. These models allow scientists to estimate crust thickness, internal temperatures, and potential depth of ice layers, providing a detailed reconstruction of the comet's physical and chemical structure. Remote measurements thus act as a window into the comet's hidden interior. Selective sublimation also informs future mission planning. If humans ever attempt sample return from interstellar objects, understanding which volatiles are accessible at the surface versus trapped beneath is critical. Targeting areas where CO2 jets expose deeper material could yield more comprehensive samples, including water ice and organics. The flyby of 3I Atlas demonstrates the necessity of multi-wavelength time-resolved observation to capture the full chemical profile. Observational strategies must account for the comet's rapid motion and limited visibility. Mars orbiters can track jets as they evolve, while infrared spectrometers measure changing volatile ratios. These coordinated observations reveal the timing of sublimation events and provide a dynamic picture of nucleus evolution. Each eruption becomes a data point in reconstructing the interior layers, turning fleeting activity into scientific insight. The selective exposure of inner layers carries implications for interpreting interstellar chemistry. Early measurements might suggest an unusual CO2:H2O ratio, but later observations show a more balanced composition as heat penetrates deeper. Recognizing this stage release prevents misinterpretation of chemical anomalies, emphasizing the importance of observing objects over time rather than relying on snapshots. How will the unfolding layers of 3I Atlas continue to reveal hidden chemistry and structural secrets as it retreats from perihelion? And what new surprises might emerge from beneath the CO2 crust? Let us take you inside the untold truth. Radiation Slowhand 3I. Atlas has spent millions of years travelling through the void between stars, exposed to a relentless bath of cosmic radiation. Galactic cosmic rays, stellar energetic particles, and high-energy photons bombard its surface, continuously altering chemical bonds and slowly reshaping the outer layers. This prolonged exposure can harden the surface, break down simple molecules, and generate complex organics that were not present during formation. Surface darkening is one visible effect of interstellar radiation. Energetic particles strike ice and dust, producing carbon-rich residues that give the comet a darker, reddened appearance. This radiation-driven crust acts as both a protective barrier and a misleading mask, concealing pristine water ice and other volatiles underneath. Observing the comet during its flyby allows scientists to estimate the thickness of this processed layer and understand the long-term effects of interstellar exposure. Radiation also drives chemical transformation. Simple ices such as CO, CO2, and H2O can undergo radiolysis, splitting into reactive radicals. These radicals recombine over time into complex molecules, including small hydrocarbons, nitrilyls, and possibly amino acid precursors. This slow chemistry, invisible in young solar system comets, provides insight into how interstellar environments contribute to the cosmic distribution of prebiotic compounds. Isotopic fractionation is another subtle consequence. High-energy particles preferentially interact with lighter isotopes, slightly altering ratios in the outer layers. Measuring these changes can inform scientists about the length of interstellar exposure, the energy spectrum of radiation encountered, and the cumulative effects on molecular stability. 3I Atlas thus serves as a natural chronometer for the chemical history of its journey. Micrometeorite impacts add another dimension. Even in interstellar space, dust grains collide with the comet at high velocities, producing localized heating, fracturing, and material redistribution. These impacts can expose deeper layers or compact surface dust, influencing sublimation behavior. Observations of jets and activity patterns during the flyby can help distinguish between radiation-induced changes and structural effects from impacts. Radiation exposure also affects volatiles differently. CO2 is more resistant to radiation damage than H2O, meaning the outer layer may become enriched in CO2 over time as water ice is partially destroyed or converted into more stable compounds. This selective survival contributes to the unusual CO2:H2O ratios observed in 3I Atlas, and offers a clue about the chemical resilience of different volatiles under long-term cosmic irradiation. Organic molecules are particularly sensitive to radiation. Small compounds may fragment, while more complex molecules once formed can remain trapped within the crust. The balance of destruction and synthesis creates a chemically heterogeneous outer layer. Spectroscopic observations from Mars orbiters or space telescopes can detect these organics in the coma, providing indirect evidence of the radiation history of the comet. Radiation-driven erosion changes the surface morphology. Continuous particle bombardment and sublimation combine to produce pits, cracks, and ridges, which influence how subsequent outgassing occurs. These structural features channel sublimating gases and dust, creating localized jets and non-uniform coma structures. Tracking these features helps reconstruct how radiation and other interstellar processes shape cometary surfaces over millions of years. Thermal cycling during perihelion interacts with radiation-processed layers. As the comet heats near the Sun, the hardened crust may crack or partially spall, exposing fresher ices underneath. This combination of cosmic processing and solar heating creates dynamic changes in the coma composition over time. Observing these changes provides a window into the cumulative effects of both interstellar and solar influences on cometary material. Radiation also has implications for isotopic and chemical fingerprints. High-energy interactions can create anomalies that must be accounted for when interpreting formation environments. Without understanding the effects of interstellar radiation, scientists might misattribute unusual isotopic ratios to exotic stellar nurseries rather than long-term cosmic processing. 3I Atlas serves as a laboratory to distinguish between primordial composition and radiation-induced evolution. The comet's journey highlights the interplay between cosmic and local effects. exposure to cosmic rays in interstellar space differs significantly from conditions within a planetary system. Comparing 3-Uptical A-Atlas to solar system comets helps isolate the unique contributions of interstellar processing. Differences in surface chemistry, organic content, and volatile ratios reveal the subtle but persistent hand of radiation shaping small bodies over astronomical timescales. Radiation also impacts the detectability of molecular emissions. Hardened outer layers can reduce the immediate release of volatiles upon solar approach, skewing observed CO2:H 2O ratios until deeper, less processed ices are exposed. Time-resolved monitoring during the flyby is therefore essential to separate radiation effects from intrinsic compositional traits. Mars orbiters and space telescopes can track these transitions, providing a multi-dimensional view of both chemistry and physics. The study of radiation effects has broader implications. Understanding how cosmic rays alter cometary material informs models of prebiotic chemistry across the galaxy. Comets like 3-Ca Atlas carry molecules that may have formed or been transformed in interstellar space, potentially contributing to the organic inventory of young planets. Observing the comet's processed layers bridges the gap between theoretical chemistry and observable cosmic phenomena. Finally, radiation history offers predictive power. By analysing surface chemistry, scientists can anticipate which layers will sublimate first, which compounds may persist, and how the coma will evolve post-perihelion. These insights enhance models for other interstellar visitors, enabling more accurate predictions of activity, composition, and observational signatures. 3-I Atlas becomes a benchmark for understanding how cosmic rays silently reshape interstellar objects over eons. What hidden transformations has radiation imposed on 3-I Atlas during its long journey? And how might these changes alter the chemical signals we observe as it passes Mars? Walk with us into the truth that was never meant to surface. One comet versus a planet. The idea of a single comet reshaping a planet's atmosphere is immediately limited by sheer scale. 3-eyed Atlas, like most comets, is tiny in comparison to Mars, with a nucleus likely measuring only a few kilometers across. Its total mass is minuscule relative to the red planet's 6.4 times 10 to the 23rd kilograms. Even if it released all its volatiles in one pass, the increase in atmospheric pressure or water availability would be negligible. To visualize this, consider the comet's volatile content. Estimates based on CO2-dominated comas suggest the total mass of outgassed material may reach only millions of tons. While large by human standards, this is vanishingly small compared to the trillions of tons of CO2 and water required to significantly alter Martian climate or create transient surface water. The flyby is an exquisite natural experiment, but not a terraforming mission. The scale disparity also affects observational interpretation. Comets may display dramatic outgassing and glowing tails that appear immense in telescope images, yet in absolute terms, these volumes are still minuscule compared to a planetary atmosphere. Misjudging scale can lead to overestimation of impact, which is why careful measurements and modelling are essential. Observers must contextualize visual spectacle with quantitative analysis. Even dust delivery illustrates the scale problem. While 3-I Atlas ejects fine particles along its trajectory, the total mass of dust is orders of magnitude below what would be required to seed global changes on Mars. Dust may locally enrich certain regions, but global redistribution is limited by planetary rotation, winds, and diffusion. The comet acts more as a tracer of material behavior than a transformative agent. Energy considerations further highlight limitations. Sublimation of volatiles releases heat and propels dust, but this energy is trivial relative to solar insolation or Martian seasonal cycles. Any interaction with Mars' thin atmosphere would produce localized effects at most, such as temporary ionization of gases or minor dust heating. But it cannot drive meaningful climate change. Scale governs feasibility. The duration of influence is also brief. 3-I Atlas passes at tens of millions of kilometers from Mars in a matter of days. The comet's proximity allows for observation, but the time window is too short for significant deposition of gases or particles. For cumulative planetary impact, repeated or large-scale delivery would be necessary. Single flybys, however spectacular, have a negligible long-term effect. Chemical dilution compounds the problem. Even if the comet releases CO2 or water efficiently, these molecules must mix into a Martian atmosphere already dominated by CO2 at 95%. The addition of a few million tons barely changes volumetric ratios, underscoring the vast difference between cometary and planetary scales. Observed emissions may be visually striking, but in atmospheric terms they are tiny. Volume and surface area also illustrate scale limits. Mars's surface spans 144 million square kilometers, meaning that any deposition from 3I Atlas disperses over an immense area. Localized jets may enhance visibility in imaging instruments, but the material thins rapidly as it spreads, diminishing practical impact. The comet's spectacular tail is impressive only against the void, not relative to planetary size. Even organics are constrained by scale. Trace molecules in the coma, while scientifically significant, represent minuscule quantities compared to the Martian crust or regolith. Any seeding effect is limited to microgram or milligram levels per square kilometre, insufficient to alter global chemical landscapes. The true value lies in what they reveal about formation, not what they can deliver at scale. From a planetary engineering perspective, the scale problem is instructive. If humanity ever considers delivering volatiles intentionally, it must account for mass, energy, and frequency requirements. 3I Atlas highlights the orders of magnitude discrepancy between what small bodies can supply and what is needed for planetary modification. This knowledge helps frame realistic expectations for long-term resource strategies. Observation strategies also reflect scale. Instruments on Mars orbiters can detect and analyze the comet's emissions precisely because the material is concentrated within the nucleus and tail. However, any attempts to extrapolate local effects to global planetary consequences would be misleading. Scientists use the comet as a chemical probe and dynamic laboratory, not as a direct agent of planetary change. Scale also affects perception. The spectacular glow of the coma and the visible dust tail can create public impressions of transformative potential, but quantitative analysis reveals the true limitations. This disparity emphasizes the importance of careful communication between scientific teams and the public, ensuring that curiosity and excitement do not morph into unrealistic expectations about planetary engineering outcomes. Comparative analysis with other interstellar objects reinforces scale considerations. Oumuamua, with no detectable coma, could contribute nothing to any planetary atmosphere, while Borisov, slightly larger than 3I Atlas, still falls orders of magnitude short of planetary impact. These examples collectively illustrate that interstellar visitors, while chemically intriguing, are inherently limited in their physical influence on worlds they pass. The scale problem also highlights scientific opportunity. While the comet cannot terraform Mars, its flyby allows researchers to test models of atmospheric interaction, dust dynamics, and gas deposition. Understanding these processes at small scales provides a template for larger-scale studies or engineered interventions, offering a controlled natural experiment that informs planetary science and exoplanetary modelling. The lesson extends beyond Mars. Any future encounter with interstellar objects should be framed in terms of chemical and observational impact rather than physical transformation. By appreciating the disproportion between comet size and planetary mass, scientists can focus on extracting maximum information from minimal material. The grandeur of the flyby lies in its ability to illuminate distant formation environments, not in its capacity to alter worlds. The scale challenge also tempers speculation about panspermia. While comets carry organics and prebiotic compounds, a single flyby delivers only trace amounts. Significant seeding of life would require either a massive flux of comets over geological timescales or targeted delivery, reinforcing the importance of understanding mass budgets and cumulative effects when evaluating interstellar contributions to planetary chemistry. How can scientists leverage the minuscule yet information-rich contribution of 3I Atlas to learn about interstellar chemistry and planetary formation without overestimating its physical impact? Follow us as the untold details rise to light. Population statistics. Are interstellar visitors common? The discovery of 3 confirmed interstellar objects in just over a decade has revolutionized our understanding of small body populations. Oumuamua, Borisov, and now 3Ds. Atlas suggests that the galaxy may be teeming with similar visitors, previously undetectable due to technological limitations. These detections force scientists to reassess the frequency and distribution of interstellar comets and asteroids. Detection biases complicate the picture. Current surveys favour fast-moving, bright objects that approach the inner solar system. Smaller, darker or more distant visitors escape notice, meaning the observed sample is likely only the tip of the iceberg. Accounting for observational biases dramatically increases estimates of the true population, hinting at a far larger number of interstellar bodies traversing space unnoticed. The role of survey technology is crucial. Instruments like Pan-STARRS, ATL-AS, and the upcoming Vera C. Rubin Observatory enhance sensitivity and sky coverage, improving the odds of catching fast, faint objects. 3i Atlas's discovery showcases how wide-field surveys coupled with rapid follow-up observations are revolutionizing our census of interstellar visitors. Detection frequency is poised to increase significantly in the coming years. Orbital dynamics help estimate population size. Hyperbolic trajectories indicate objects are not gravitationally bound to the Sun, allowing scientists to model the density of interstellar material passing through the solar system. By calculating the flux needed to observe 3 objects within a decade, researchers derive a rough estimate of millions of interstellar small bodies crossing planetary space annually, most of which remain undetected. Size distribution is another key factor. Interstellar objects range from tiny meter-scale rocks to kilometer-scale comets. Larger objects like Borisov are easier to detect but rarer, while smaller fragments may be extremely numerous yet invisible. Understanding the distribution of sizes informs models of ejection from planetary systems and the prevalence of debris in interstellar space, allowing scientists to predict detection probabilities for future encounters. Ejection mechanisms influence population density. Planetary scattering, close stellar encounters, and disk instabilities can send bodies into interstellar space. Simulations of planetary system formation suggest that many systems expel a significant fraction of their minor bodies. 3i Atlas serves as a case study confirming that these processes are active across the galaxy, producing a steady stream of chemical messengers travelling between stars. The observed chemical diversity also informs statistics. CO2-rich comets like 3i Atlas contrast with water-dominated bodies, these such as Borisov, implying that interstellar populations are chemically heterogeneous. This diversity complicates attempts to generalize about interstellar visitors, but also provides rich datasets to probe formation environments across multiple stellar systems. Each detection adds a new dimension to the census. Gravitational focusing by the Sun and planets affects detection rates. Incoming interstellar objects are subtly redirected, increasing the likelihood that larger bodies enter the inner solar system. This effect must be included in population estimates, as observed numbers are biased toward trajectories that make them detectable. Correcting for these factors suggests a far more populous interstellar object community than raw discovery rates indicate. Statistical modelling also considers temporal sampling. Surveys do not continuously cover the entire sky. Observing gaps mean transient interstellar objects may go unnoticed. 3i Atlas's timing near Mars' orbit highlights how serendipity affects discovery, reinforcing that detection counts underrepresent the true population. Continuous high-sensitivity monitoring will refine estimates and reveal patterns in arrival rates and trajectories. Comparisons with other star systems provide additional context. Models of planetary formation in nearby systems predict the ejection of billions of minor bodies over their lifetimes. If even a tiny fraction pass through our solar system, the probability of detection over the past decade aligns with current observations. 3i Atlas thus validates theoretical predictions and supports the notion of a steady interstellar influx of material. Impact probability calculations further contextualize findings. Even though interstellar comets are numerous, their high velocities and hyperbolic orbits minimize collision risk with planets. Most pass unnoticed or unmeasured, emphasizing the difference between detection and actual planetary effect. Observational campaigns benefit more from chemical analysis than from anticipating impacts. Technological improvements will continue shaping the population picture. Advanced surveys capable of detecting smaller and fainter objects, coupled with artificial intelligence for rapid identification, promise to uncover hundreds or thousands of previously hidden interstellar visitors. Each new detection refines statistical models and deepens our understanding of galactic small body dynamics. The implications for planetary science are profound, each object provides a snapshot of a distant star system's chemical and physical history. Understanding how many interstellar visitors exist allows scientists to estimate the frequency with which exogenous material reaches planetary surfaces, offering a broader perspective on cosmic chemical exchange and potential panspermia scenarios. Observational campaigns can also prioritize chemical characterization over mere detection. 3i Atlas's unusual CO2:H2O ratio highlights the value of identifying composition quickly. By combining trajectory analysis with chemical signatures, researchers can target follow-up strategically, enhancing the scientific payoff of each detection. This approach maximizes the utility of limited observation windows. If millions of interstellar visitors traverse the solar system each year, how many more hidden comets and asteroids are silently passing through, carrying secrets of distant worlds yet to be discovered? Come along as we uncover the hidden story. Spectroscopy under pressure. Spectroscopy is the cornerstone of compositional analysis for distant objects, but interpreting data from interstellar visitors like 3i Atlas is far from straightforward. Instruments measure the absorption and emission of light across different wavelengths, producing spectra that encode molecular signatures. Yet these signals are subtle, easily distorted by instrumental limitations, atmospheric interference, or dust contamination, creating uncertainties that must be carefully managed. One major challenge arises from the comet's rapid motion relative to Earth and Mars. Doppler shifts can alter the apparent wavelength of emissions, potentially confusing spectral lines. Observers must correct for this motion to accurately identify molecules such as CO2, H2O, or cyanides. Even small errors in velocity correction can mimic or mask real chemical features, requiring precise timing and repeated measurements. Dust interference compounds spectral uncertainties. Cometary dust scatters sunlight, producing a continuum signal that can obscure weak molecular lines. For 3i Atlas, the dense CO2-driven jets eject fine particles which scatter across the coma. Differentiating dust-induced features from genuine molecular emissions demands sophisticated modelling and multi-wavelength observations, ensuring that chemical conclusions are not artefacts of optical scattering. Instrumental noise also poses challenges. Space telescopes and orbiters rely on detectors with finite sensitivity and calibration limits. Variations in detector response, cosmic ray hits on sensors, and thermal noise can all introduce spurious signals. Researchers mitigate these effects through calibration, repeated exposure, and cross-validation between instruments, yet residual uncertainty always persists, particularly for faint interstellar objects. Atmospheric interference is another complicating factor for ground-based observatories. Even at high altitudes, water vapor and CO2 in Earth's atmosphere absorb strongly in key spectral bands, potentially blending with signals from 3i Atlas. Adaptive optics, spectral modelling, and simultaneous observations from multiple sites help isolate cometary features, but complete removal of atmospheric contamination is impossible, emphasizing the value of space-based platforms. Rapid evolution of the comet's coma adds temporal complexity. As 3i Atlas approaches perihelion, the relative intensity of CO2, water, and minor organics shifts dynamically. A spectral snapshot at one moment may not represent the overall composition. Time-resolved spectroscopy becomes essential to capture the true behavior of the comet, revealing both dominant volatiles and transient species released from underlying layers. Signal overlap is another concern. Certain molecules emit at similar wavelengths, creating blended features that can be misinterpreted. For example, cyanide emissions overlap with certain CO bands, complicating identification. Advanced spectral deconvolution techniques and laboratory reference spectra help resolve ambiguities, but the risk of misassignment underscores the importance of caution in interpreting chemical data. Calibration standards are critical to accuracy. Observers use stars of known composition to benchmark instruments, but variations in calibration procedures or environmental conditions can introduce subtle discrepancies. For interstellar comets moving rapidly through the sky, calibration must be performed frequently and with high precision, as even small errors can skew conclusions about volatile ratios or chemical anomalies. Signal-to-noise ratio limitations define detection thresholds. Weak molecular lines may be buried under background noise, particularly for minor organics or isotopic variants. Increasing exposure time can improve detectability, but the comet's motion and changing geometry constrain observation windows. Understanding these limits ensures that reported chemical features reflect real signals rather than artifacts of insufficient data. Spectral contamination can also come from interplanetary material. Dust or gas along the line of sight may add extraneous absorption or emission lines, particularly in ultraviolet and infrared wavelengths. Differentiating cometary signals from background sources requires careful modelling and cross-referencing with prior observations of the same region of space. Accurate identification depends on both observational rigour and interpretive care. Observational geometry influences spectral clarity. The phase angle, distance from the Sun, and relative position of the comet to Earth or Mars determine which layers of the coma are illuminated and which molecules are detectable. Certain volatile emissions may be shadowed or diluted, creating an incomplete or biased spectral profile. Multi-angle observations improve completeness and reduce interpretive uncertainty. High-resolution spectroscopy is particularly valuable. By resolving narrow molecular lines, scientists can identify isotopic variants and subtle chemical differences. For 3 Atlas, such measurements could distinguish between formation environments, radiation processing, and surface layering effects. Achieving this resolution requires precise instrumentation and stable platforms, emphasizing the technical sophistication required for accurate interstellar analysis. Cross-instrument validation is another safeguard. Comparing spectra from JWST, SPHEREX, and Mars orbiters provides redundancy and confirmation, helping separate real molecular features from artifacts. Discrepancies can reveal potential errors, while consistent signals strengthen confidence in chemical assignments. This multi-platform approach is essential for robust characterization of interstellar objects. Ultimately, understanding the limits of spectroscopy informs how discoveries are communicated. The unusual CO, 2:H2O ratio in 3IA, Atlas for example, is compelling, but must be contextualized within uncertainties, measurement biases, and evolving coma dynamics. Communicating both findings and limitations preserves scientific integrity and prevents misinterpretation by the public or media. The dynamic nature of 3 Atlas, combined with observational challenges, underscores the value of repeated, time-resolved spectroscopy across multiple wavelengths. By accounting for motion, dust, atmospheric interference, and instrumental limits, scientists can build a more complete picture of the comet's true chemical composition. This approach transforms a fleeting flyby into a detailed laboratory for interstellar chemistry. How will the careful disentangling of these uncertainties refine our understanding of 3I Atlas's chemical signature? And what unexpected compounds might yet emerge once the noise and artifacts are fully accounted for? Stay with us to uncover what comes next. Why some objects spark alien theories. When Oumuamua was first detected, its peculiar trajectory sparked worldwide fascination. A non-gravitational acceleration component seemed to push it beyond the influence of the Sun alone, prompting speculation about artificial propulsion or alien origins. 3 Atlas, while less extreme in its motion, invites similar scrutiny, illustrating how natural mechanisms can masquerade as anomalies. Outgassing is the primary natural explanation for unexpected acceleration. Jets of gas and dust escaping from the nucleus create minute but measurable thrust. For comets with irregular shapes or highly localized sublimation, these forces can alter the trajectory without requiring any exotic mechanism. 3R Atlas's CO2-dominated outgassing provides a textbook example, showing that even interstellar bodies can experience noticeable yet natural acceleration. Shape and rotation influence acceleration signatures. Non-spherical comets spinning along uneven axes produce anisotropic ejection of gas. This directional emission can mimic the appearance of continuous propulsion, particularly when observed from a fixed point on Earth or Mars. For 3I Atlas, combining shape modelling with emission mapping clarifies that apparent anomalies arise from geometry rather than external manipulation. Thermal lag also plays a role. Heat absorbed on the sunward side takes time to reach deeper layers, producing delayed sublimation. This lag creates transient accelerations that may seem unexplained without detailed thermal modelling. Observing 3I Atlas's comet evolution provides an opportunity to correlate outgassing patterns with trajectory deviations, reinforcing natural explanations over speculative ones. Dust molecule interactions add subtle effects. As gas escapes, it can entrain small dust grains, adding mass and altering momentum transfer. These microscale interactions contribute to the apparent non-gravitational acceleration. Spectroscopic monitoring and dust modelling allow scientists to account for this effect, ensuring that trajectory analysis reflects physical reality rather than observational artifact. Observational geometry affects perceived anomalies. The relative positions of the comet, Earth, Mars and Sun influence apparent motion. Slight differences in measurement angles or timing can exaggerate deviations, particularly for fast-moving interstellar objects. Careful triangulation and multi-platform tracking are essential for distinguishing real accelerations from geometric illusions. Historical context provides perspective. Comets in the solar system have displayed subtle non-gravitational effects for centuries, often attributed to uneven sublimation. 3I Atlas is simply the first opportunity to observe such processes in an interstellar object with modern instrumentation. Recognizing this continuity helps prevent sensational interpretation while appreciating the scientific significance. Spectral data supports natural acceleration hypotheses. By correlating observed jets with momentum changes, scientists can calculate the expected effect on the comet's path. 3I Atlas's CO2 jets, precisely measured by orbiters and telescopes, account for the observed trajectory shifts without invoking exotic propulsion. This reinforces the principle that extraordinary claims require extraordinary evidence. Public fascination with acceleration anomalies often stems from visual perception. The dramatic tails, bright jets, and rapid motion create an impression of intentional movement. Social media amplifies these perceptions, connecting them to narratives of extraterrestrial technology. 3I Atlas highlights the need for careful communication to separate spectacular imagery from scientific inference. Acceleration studies also reveal internal properties. Measuring thrust produced by outgassing allows estimates of nucleus density, porosity, and volatile distribution. For 3 Atlas, this analysis informs models of surface layering, thermal conductivity, and internal structure, providing insight into both formation and evolutionary history. Unexpected motion thus becomes a diagnostic tool rather than a mystery. Radiation pressure contributes marginally to acceleration. Small dust grains experience force from sunlight, nudging them slightly along the comet's path. While negligible for a dense nucleus, this effect can alter coma dynamics and contribute to apparent deviations. Accounting for radiation pressure refines trajectory predictions and strengthens natural explanations for observed motion. Rotation-induced centrifugal effects further complicate motion analysis. As 3I Atlas spins, surface material can migrate, causing localized eruptions of gas and dust. These eruptions act as miniature thrusters, subtly adjusting the comet's velocity. High-resolution imaging of active jets enables scientists to correlate rotational dynamics with acceleration signatures, reinforcing mechanistic understanding. Thermal sublimation asymmetries produce long-term trajectory changes. Comets approaching the Sun from steep angles may release more volatiles on one side, creating persistent directional thrust. Observing how 3I Atlas's CO2 emissions vary with solar exposure allows prediction of these minor accelerations, demonstrating that even interstellar comets obey classical physics. Outgassing and acceleration analysis also inform planetary protection and hazard assessment. Understanding the physical forces at work helps predict paths for future interstellar objects, providing context for impact probability and observational planning. 3I Atlas becomes a case study in separating physical reality from sensationalized speculation. If natural forces can so convincingly mimic mysterious propulsion, what other hidden mechanisms might shape interstellar objects in ways we have yet to fully understand? Let us take you through the secrets. Organics on the wind, panspermia possibilities. The concept of panspermia suggests that life, or its building blocks, can travel between stars via comets, asteroids, or interstellar dust. 3I Atlas, carrying a mixture of CO2, water, and trace organics, offers a natural laboratory to explore this idea. Even minute quantities of organic molecules delivered to planetary surfaces over millions of years could provide the raw materials for chemical evolution. Studying interstellar comets offers a distinct edge over solar system bodies in panspermia research. Unlike local comets, they hail from distant star systems, potentially bearing molecular signatures completely unfamiliar to our solar neighbourhood. 3I Atlas presents a rare chance to identify compounds formed under different astrophysical conditions, increasing the known chemical diversity and deepening our understanding of prebiotic chemistry. Chemical stability during interstellar travel is a central question. Cosmic radiation, vacuum exposure, and thermal cycling can degrade sensitive molecules. Yet certain organics, such as polycyclic aromatic hydrocarbons, nitriles, and amino acid precursors, exhibit remarkable resilience. 3I Atlas's composition hints at the survival of complex organics over millions of years, supporting the feasibility of natural interstellar delivery of biologically relevant compounds. Delivery mechanisms to planetary surfaces are equally important. Even though 3I Atlas will not directly impact Mars, dust grains and sublimated molecules from its coma can intersect planetary atmospheres. These fine particles may deposit trace organics, offering insight into how interstellar objects could contribute to chemical enrichment, even in small, localized quantities. Thermal protection plays a crucial role. Cometary material is often embedded in ice matrices, shielding organics from radiation damage. As sublimation occurs near perihelion, these compounds can be gradually released without complete destruction. Studying 3I Atlas's outgassing allows scientists to model how interstellar organics could survive both space transit and atmospheric entry on planetary surfaces. Isotopic analysis strengthens the panspermia hypothesis. Variations in carbon, nitrogen, and oxygen isotopes can trace the origin of molecules and the environments in which they formed. For 3I Atlas, measuring isotopic ratios remotely provides clues about interstellar chemistry and the likelihood that its organics are genuinely exotic, rather than products of solar system contamination. The size and mass of particles matter. Micron-scale dust grains can penetrate atmospheres without significant heating, delivering intact organics to the surface. 3I Atlas's fine dust tail represents a natural mechanism for seeding, even if in extremely low concentrations. This process demonstrates that interstellar material can bypass destructive entry effects that would otherwise degrade complex molecules. Temporal aspects of deposition are critical. Interstellar objects like 3I Atlas move quickly, meaning that any material reaching a planet's surface is transient and sporadic. While the impact of a single flyby is negligible on a global scale, cumulative effects over millions of years could deliver measurable quantities of organics. This concept reframes our understanding of the slow but persistent enrichment of planetary surfaces by interstellar visitors. Radiation-induced chemical evolution during transit can generate new molecules. Cosmic rays and ultraviolet photons may transform simple ices into more complex organics, enhancing the chemical diversity delivered to planets. Observing 3I Atlas's coma provides a snapshot of both primordial molecules and those altered by interstellar processing, offering direct evidence of natural molecular evolution in space. The survival of organics also depends on comet composition. CO2-rich comets like 3I Atlas may provide a more protective environment for embedded molecules than water-dominated bodies, as CO2 sublimates at lower temperatures and can shield organics until closer to a star. This selective survival has implications for the types of molecules delivered to planets in interstellar panspermia scenarios. Spectroscopic detection of organics in the coma informs models of delivery potential. JWST and Mars orbiters can identify faint molecular features, mapping the distribution of complex organics. Even transient signatures reveal the types and abundance of molecules capable of surviving interstellar transit, providing data critical to evaluating the plausibility of panspermia. Comparisons with solar system comets highlight differences in chemical cargo. Whereas most known comets exhibit water-dominated comas, 3I Atlas's CO2-rich composition suggests a different formation environment. This diversity underscores the potential for interstellar objects to expand the range of molecular building blocks available to planets, providing a richer substrate for prebiotic chemistry. If interstellar dust and comets can quietly seed planets over eons, what unseen chemical legacies might already be shaping worlds across the galaxy? Let us take you inside the untold truth. The fingerprints of birthplaces. Isotopic ratios act as natural barcodes for tracing the origin of celestial objects. For interstellar visitors like 3i Atlas, isotopes of carbon, oxygen, nitrogen, and hydrogen provide crucial clues about the star system in which they formed. Variations from solar system norms signal processes or environments unique to distant planetary nurseries, offering a rare glimpse into the chemistry of other stars. The ratio of carbon isotopes, 12C to 13C, reflects stellar nucleosynthesis conditions. A comet with elevated carbon-13 may indicate formation around a star with a particular mass or metallicity. Spectroscopic measurements of 3 Atlas's coma, when combined with modelled absorption lines, allow scientists to infer these ratios remotely, providing insights into the stellar environment that shaped its chemistry. Oxygen isotopes, particularly 16O, 17O and 18O, reveal the temperature and radiation environment during formation. Ratios deviating from solar system norms suggest exposure to unique cosmic rays or stellar winds. For 3i Atlas, analysing oxygen isotope ratios can help identify whether the comet formed in a cold outer disk, near a CO2 ice line, or in regions rich in energetic particles. Nitrogen isotopes provide complementary information about volatile chemistry. 14N/15N ratios vary with planetary system evolution, disk processing, and interstellar enrichment. Differences in nitrogen isotopes among comets, asteroids, and interstellar objects inform models of chemical fractionation. Detecting unusual ratios in 3i Atlas could indicate formation environments markedly different from our own solar system. Hydrogen isotopes, including the deuterium to hydrogen ratio D/H, offer key insights into water ice origin. Elevated D/H ratios point to colder, more distant formation regions where fractionation processes preferentially enrich deuterium. Measuring D/H in 3i Atlas, even remotely through infrared spectroscopy, provides a direct connection to the conditions of its birthplace, offering evidence for its interstellar provenance. Isotopic fingerprints also shed light on processing after ejection. Cosmic rays, UV irradiation, and collisions in interstellar space can subtly alter ratios over time. Observing 3i Atlas's isotopes helps separate primordial composition from interstellar alteration, allowing scientists to distinguish between birth environment signatures and post-ejection modifications, which is crucial for accurate modelling. Analytical challenges arise from the comet's rapid movement and faint emission lines. High-resolution spectrometers, such as those aboard JWST or Mars orbiters, are needed to resolve subtle isotopic shifts. Careful calibration and long exposure integration improve signal-to-noise ratios, enabling detection of rare isotopic species that carry the most informative clues about origin. Comparisons with solar system comets establish baselines. Most known comets have been measured for key isotopic ratios, providing a reference framework. 3i Atlas's divergence from these ratios confirms its interstellar nature and highlights the diversity of chemical environments across the galaxy. Each discrepancy in isotopes is a message from another stellar system waiting to be decoded. The CO2-rich composition of 3i Atlas amplifies the value of isotope studies. Carbon and oxygen isotopes in CO2 molecules reflect formation at specific temperatures and distances from the host star. By mapping isotopic ratios alongside volatile abundances, scientists can reconstruct not only where the comet formed, but also the chemical gradients present in its birth disk. Understanding isotopic patterns informs theories of planetary system evolution. The ratios in 3i Atlas suggest that material ejection is common across a range of stellar environments, with comets acting as natural messengers carrying chemical fingerprints of their original disks. This has implications for galactic chemical evolution and the distribution of prebiotic compounds in the universe. Isotopic evidence also contextualizes panspermia potential. Molecules preserved during interstellar travel carry not only structural information, but isotopic memory, offering clues about the broader galactic distribution of life-forming chemicals. 3i Atlas exemplifies how isotopic study can bridge chemistry, astrophysics, and astrobiology, revealing the journey of material across light years. Remote isotope detection is not perfect, but advances in spectroscopy allow reasonable constraints. Comparing isotopic ratios to theoretical models provides probabilistic assessments of origin, helping distinguish between formation zones in inner versus outer disks, cold versus warm regions, and high radiation versus shielded environments. Each measurement refines our understanding of distant star systems. By integrating isotopic data with other cometary characteristics, composition, outgassing behavior, and tail morphology, researchers can construct a holistic picture of 3I Atlas. This synergy transforms fleeting observations into a detailed narrative of birth, ejection, and interstellar survival, emphasizing the detective work inherent in modern planetary science. If isotopic ratios act as cosmic fingerprints, what hidden stellar stories are encoded in the 3I Atlas, waiting to be uncovered and compared with other interstellar visitors? Come with us to know more. Dust sampling from orbit. Dust sampling offers a practical method to study interstellar objects without the logistical nightmare of a close intercept mission. As 3I Atlas passes near Mars, orbiters can target its coma and tail, capturing fine particles carried along by CO2 jets. Even tiny grains hold valuable chemical and isotopic information, providing insights into the comet's origin and the processes it has undergone during interstellar travel. Mars orbiters, such as the Trace Gas Orbiter and Mars Express, have instruments capable of detecting and analysing dust in situ. Dust analyzers and mass spectrometers can measure elemental composition, isotopic ratios, and organic content. While the comet's proximity is still tens of millions of kilometers, careful trajectory planning and high-precision instruments allow for meaningful collection of particles intersecting the spacecraft's path. The primary challenge is particle capture without contamination. Instruments must distinguish cometary grains from background dust, spacecraft outgassing, and solar wind particles. Techniques such as aerogel collection or electrostatic dust traps can gently capture grains while preserving their structure and chemistry. Preserving delicate organics is particularly crucial, as they may provide clues about the comet's interstellar formation environment. Remote sensing complements physical collection. Optical and infrared imaging, combined with spectrometry, identifies the densest regions of the coma and predicts where dust concentrations are highest. By modelling 3I Atlas's jets and outgassing patterns, scientists can target optimal interception windows, maximising the likelihood of collecting pristine samples in a brief observational period. Even microscopic particles carry significant information. Trace organics, carbonaceous material, and isotopic signatures provide a chemical snapshot of the comet's history. Comparing these with laboratory simulations of interstellar processing allows scientists to infer radiation exposure, thermal history, and volatile retention. Each captured grain becomes a time capsule from another star system, offering a tangible connection to distant astrophysical processes. Safety and instrumentation limits constrain the scope of collection. High-speed grains can damage detectors or degrade organic compounds. Sampling strategies must balance proximity, collection time, and velocity to avoid destruction. Mars orbiters, moving at orbital speeds, can synchronize measurements with predicted dust streams to optimize the chances of successful, minimally destructive sampling. Data gained from dust sampling informs more than chemistry. It reveals the structure of the coma and the dynamics of ejected material. Observing particle size distribution, density, and motion allows researchers to infer sublimation rates, jet activity, and the layering of volatile rich regions. These parameters refine models of cometary evolution in interstellar space. Cumulative collection over multiple flybys or missions can build a statistically significant dataset. While a single encounter may yield only a few particles, repeated observations of interstellar comets enhance understanding of population-wide properties. 3I Atlas thus serves as both a pilot experiment and a benchmark for future dust sampling campaigns. Ultimately, dust sampling bridges the gap between remote observation and laboratory analysis. It provides tangible evidence of interstellar chemistry, complements spectroscopic measurements, and allows the study of materials that have travelled millions of light years. Every grain captured is a fragment of a foreign world, arriving in our solar system to tell a story. If tiny dust grains can carry the secrets of distant star systems, what hidden chemical archives might 3I Atlas deposit in our orbiter's instruments, waiting to reveal the history of a faraway birth? Let us take you where the story turns shocking. The perfect window. Solar conjunction creates a natural observational blackout, a phenomenon that has both frustrated and fascinated astronomers. For 3 Atlas, this occurs when the comet's position aligns closely with the Sun as seen from Earth, making optical and radio tracking nearly impossible. The Sun's overwhelming glare masks the comet, leaving a temporary gap in continuous monitoring that tests both instrumentation and patience. This observational blackout has practical consequences for data collection. Earth-based telescopes lose the ability to measure brightness, tail morphology, and spectral features. Even advanced techniques such as coronagraphy and adaptive optics struggle to isolate faint cometary signals from the Sun's intense radiation. During this window, scientists rely heavily on predictive models and prior observations to estimate the comet's behaviour. Mars offers a unique observational advantage during Earth's blind period. The planet's orbit provides a different viewing angle, allowing orbiters to capture data inaccessible from Earth. Instruments on Mars Express or the Trace Gas Orbiter can monitor the comet's coma, outgassing patterns, and dust distribution, partially compensating for the gap in terrestrial coverage. This dual perspective underscores the strategic importance of multi-planet monitoring. Predictive modelling becomes essential when direct observation is blocked. Trajectory projections, outgassing estimates, and dust tail simulations allow scientists to anticipate comet behaviour during the conjunction window. By integrating prior measurements with physics-based models, researchers can forecast changes in coma composition and jet activity, ensuring that observational campaigns remain informative despite the temporary blackout. The blackout period also highlights the limits of remote observation. Even space telescopes must contend with solar proximity, where scattered light and thermal effects interfere with sensitive instruments. 3I Atlas's alignment emphasizes the need for flexible planning, cross-platform coordination, and adaptive strategies in cometary science, where timing and geometry dictate access to critical data. Interestingly, this privacy can be scientifically advantageous. Temporary observational gaps prevent overinterpretation of transient features, encouraging researchers to focus on reproducible trends and long-term behaviour. In the case of 3I Atlas, the conjunction provides a natural control period, isolating solar-driven effects and offering insight into baseline coma chemistry absent immediate observational interference. Communication strategies during conjunction are also vital. Public and media interest often spikes during interstellar events, and the lack of real-time data can lead to speculation. Agencies must clearly explain observational limitations, expected blackout duration, and ongoing efforts from alternative platforms. Transparency maintains credibility while emphasizing that gaps do not equal loss of scientific opportunity. This period also allows anticipation of post-conjunction observations. Once 3I Atlas emerges from solar alignment, changes in brightness, tail structure, and chemical composition can be compared with models generated during the blackout. Deviations reveal dynamic processes that were occurring unseen, turning a period of apparent inactivity into a valuable window for testing predictive accuracy. If alignment with the Sun can obscure an interstellar visitor, what secrets might emerge once the comet slips back into full view, ready to reveal the changes hidden during its period of cosmic privacy? Stay with us to uncover what comes next. Narrative viruses. Scientific uncertainty is fertile ground for speculation, and interstellar visitors like 3I Atlas are no exception. As data trickles in, social media amplifies early findings, often framing minor anomalies as dramatic mysteries. A slight deviation in trajectory, a surprising CO, 2, H, 2O ratio, or an unusual green glow can quickly evolve into viral narratives that distort public perception. Misinformation spreads rapidly due to the fragmented nature of online platforms. Tweets, short videos, and sensational headlines often emphasize what is unknown rather than what is measured. Even well-intentioned reporting can exaggerate gaps in data, creating a sense of imminent revelation or conspiracy. The story of 3I Atlas illustrates how easily scientific nuance can be lost in translation. Scientific agencies face a delicate balancing act. Transparency demands sharing discoveries in real time, but incomplete data can fuel misinterpretation. NASA, ESA, and other organizations use press releases, blogs, and public briefings to provide context, explain observational limitations, and correct misconceptions. Communication strategies increasingly rely on clarity, consistency, and timely updates to counteract the momentum of viral speculation. Confirmation bias further accelerates narrative formation. Audiences may interpret ambiguous observations to fit preconceived ideas about alien life, government secrecy, or cosmic mysteries. Social media algorithms amplify content that provokes emotion, favouring dramatic claims over measured analysis. Scientists studying 3i Atlas must anticipate these biases when framing public messaging. Interactive engagement offers both challenges and solutions. Live Q&A sessions, explainer videos, and transparent data sharing can mitigate misinterpretation while fostering trust. By guiding public curiosity with evidence-based explanations, researchers transform passive speculation into informed inquiry, helping the audience appreciate the scientific process behind 3i Atlas observations. Miscommunication can also influence funding and research priorities. Viral narratives may pressure agencies to prioritize rapid public-facing results over careful analysis, potentially compromising methodological rigor. Balancing public interest with scientific integrity is a subtle, ongoing negotiation, particularly during high-profile flybys where global attention is intense. Historical context highlights recurring patterns. Past interstellar visitors, including Oumuamua and Borisov, experienced similar cycles of sensationalism followed by tempered scientific interpretation. The pattern demonstrates that public fascination is predictable and underscores the need for preemptive communication planning in upcoming missions observing 3i Atlas. Narrative viruses are not entirely negative. Heightened attention can increase support for space science, generate new collaborations, and inspire educational engagement. The challenge lies in channeling curiosity constructively, turning viral interest into opportunities for public understanding rather than misunderstanding or alarmism. Data visualization plays a critical role in shaping perception. Clear graphs, annotated imagery, and comparative charts help audiences distinguish between observed facts and theoretical interpretation. For 3i Atlas, visual tools elucidate coma composition, trajectory, and observed anomalies, reducing reliance on narrative alone to convey scientific significance. If social media can turn subtle observations into cosmic mysteries, how might carefully crafted scientific communication shape the next chapter in 3i Atlas's story, guiding curiosity without distortion? Come along as we uncover the hidden story. Design versus emergence. The universe often presents patterns that appear intentional yet arise naturally from physical laws. Interstellar objects like 3i Atlas provide a canvas to explore this tension. From a distance, its unusual CO2-rich composition and green coma may suggest deliberate construction, but careful analysis points to emergent phenomena shaped by chemistry, radiation, and orbital dynamics. Emergent behavior in comets arises from simple physical processes interacting over time. Sublimation, jet formation, and dust ejection follow predictable thermodynamic and gravitational principles, yet produce complex, seemingly designed structures. 3i Atlas exemplifies how straightforward mechanisms yield intricate outcomes, emphasizing that apparent purpose does not imply intent. Patterns in chemical composition also challenge perception. The CO2:H2O ratio, unusual to Earth-based observers, is the natural result of formation near a CO2 ice line and subsequent interstellar processing. Such patterns demonstrate that observational anomalies can arise from environmental conditions rather than external intervention, illustrating the principle of emergence at cosmic scales. Orbital dynamics further illustrate natural design. Hyperbolic trajectories, high eccentricity, and solar flybys create visually dramatic paths, yet are dictated by gravitational physics. The cinematic movement of 3i Atlas is an emergent outcome of an initial ejection velocities and interstellar travel, highlighting how deterministic processes can mimic intentional choreography in the cosmos. Even spectral signatures convey emergent patterns. Green fluorescence from dicarbon and cyanide arises from photochemical reactions, not construction. Light scattering and molecular excitation naturally produce visual effects that appear remarkable but are fully explainable. Observing 3i Atlas in multiple wavelengths confirms that its striking appearance is a consequence of chemistry and radiation exposure. Philosophical reflection emerges from this interplay. Humans are predisposed to seek meaning, projecting intention onto complex systems. Studying 3i Atlas invites consideration of how perception influences interpretation, reminding us that the line between observed pattern and inferred purpose is often a cognitive construct rather than a cosmic truth. Complexity in small systems reinforces the principle. Even minor variations in nucleus shape, rotation, and outgassing can create behaviours that seem directed. 3I Atlas's jet patterns, tail symmetry, and coma structure reveal rich dynamics without requiring intelligent causation, providing a case study in emergent complexity from simple rules. Comparative analysis with other interstellar visitors strengthens understanding. Oumuamua's acceleration controversy, Borisov's water-rich coma, and now 3I Atlas's CO2 dominance illustrate diverse outcomes under similar physical laws. Recognizing shared mechanisms amidst differing results highlights the universality of emergence in shaping cosmic phenomena. Considering emergence versus design also impacts scientific interpretation. Prematurely attributing unusual features to external intelligence undermines rigorous methodology. 3I Atlas reminds researchers that the most extraordinary observations can have ordinary explanations when viewed through a lens of physics, chemistry, and environmental context. Ultimately, recognizing emergence only heightens our sense of wonder. The natural processes shaping interstellar objects create patterns as captivating as any deliberate design. Studying 3I Atlas offers insight into the interplay of chance, physical laws, and environmental factors, enriching both scientific understanding and philosophical reflection. While patterns arise naturally, the responsibility to interpret their meaning rests with us. If nature alone can sculpt such complexity across light years, what does 3I Atlas teach us about recognizing true design in a universe ruled by emergent forces? Stay with us to know. Planetary protection and ethical boundaries. Interstellar comets like 3I may Atlas challenge traditional frameworks for planetary protection. While solar system missions focus on preventing contamination of Mars or Europa, interstellar visitors carry unknown organics and dust that could influence surface chemistry naturally. Understanding these interactions is crucial for updating protocols and ethical guidelines for future exploration. The potential for natural delivery of organics raises difficult questions. If comets can deposit amino acids, nitriles, or other prebiotic molecules on planets, distinguishing between naturally introduced compounds and contamination from human missions becomes essential. 3I Atlas offers a live case study of how interstellar material intersects with planetary environments, prompting re-evaluation of detection criteria. Ethical considerations extend beyond contamination. Deliberately interacting with interstellar objects, whether through orbiters, landers, or sample collection, introduces human influence into systems that would otherwise remain untouched. Even non-invasive dust sampling carries potential for altering particle trajectories or introducing Earth-originating material, demanding careful assessment of risk versus scientific benefit. Policy frameworks must weigh curiosity against caution. Agencies like NASA, ESA, and JAXA maintain strict guidelines for sample return missions, but interstellar objects introduce new uncertainties. Unlike solar system comets, their unknown chemical inventory could interact unpredictably with planetary atmospheres or surfaces, creating a grey area in existing planetary protection protocols. The temporal aspect is significant. Interstellar objects traverse planetary orbits quickly, meaning their interaction window is brief. This limits the potential for contamination, but also restricts observation time. Any policy updates must consider both the fleeting nature of these encounters and the opportunity to gather critical data without compromising planetary integrity. Risk assessment tools can model potential outcomes. By simulating deposition of dust and organics from 3I Atlas onto Mars or other bodies, scientists can quantify likelihoods of chemical alteration, contamination, or false positives in life detection experiments. These models inform guidelines, helping establish thresholds for permissible interaction with interstellar visitors. Scientific collaboration is central to ethical decision-making. International coordination ensures that actions taken by one agency do not compromise global objectives. 3I Atlas demonstrates the value of shared protocols for interstellar objects, where multiple orbiters, telescopes, and researchers can pool data while minimizing the risk of unintended consequences. The question of intrinsic value arises alongside planetary protection. Should an interstellar object, as a unique messenger from another system, be preserved in its natural state? Ethical frameworks increasingly recognize the importance of respecting rare cosmic phenomena while still pursuing scientific knowledge, balancing exploration with stewardship. Monitoring post-flyby impacts informs ongoing ethical practice. Observations of 3I Atlas after perihelion can reveal whether natural dust deposition influenced planetary surfaces or instruments. This feedback loop helps refine protective measures for future interstellar encounters and establishes benchmarks for responsible research. By integrating scientific insight, policy guidance, and ethical reflection, planetary protection strategies evolve to meet the challenges of a universe increasingly accessible to observation. 3I Atlas teaches us that even passive interstellar visitors demand careful consideration, reminding humanity of its responsibility in handling cosmic interactions. If interstellar objects naturally deliver organics across the galaxy, how should humanity define its boundaries for intervention? And where does responsible curiosity meet ethical restraint? Stay with us to uncover what comes next. Why we can't chase it. Technical limits on intercepts. Interstellar objects like 3I Atlas travel at velocities far exceeding those of conventional solar system bodies. With speeds typically tens of kilometers per second relative to the Sun, these objects move faster than most spacecraft can achieve without extreme propulsion. This makes distant interception a monumental engineering challenge, highlighting the limits of current technology. Trajectory timing is a critical obstacle. Even a modest delay in launch can result in missing the flyby entirely, as 3I Atlas covers millions of kilometers in a matter of weeks. Precise calculations are necessary to plan an intercept, yet orbital uncertainties and small perturbations can make accurate targeting extremely difficult, leaving very narrow launch windows. Propulsion technology remains a limiting factor. Conventional chemical rockets cannot accelerate fast enough to match the hyperbolic velocity of interstellar objects. Even advanced ion or solar sail concepts face challenges due to the enormous energy requirements and time needed to achieve comparable speeds, particularly for missions originating from Earth. Fuel and mass constraints compound the problem. Carrying sufficient propellant for high-speed maneuvers significantly increases spacecraft mass, which in turn demands more powerful launch vehicles and escalates cost. The trade-off between onboard instruments and propulsion capacity restricts the feasibility of rapid response missions to fast-moving interstellar visitors. Navigation and guidance pose additional hurdles. Interstellar objects have unpredictable outgassing patterns that can subtly alter their trajectory. Spacecraft must be equipped with autonomous navigation systems capable of compensating for small, sudden changes in course, adding complexity and cost to any potential intercept mission. Communication lag is another factor. Deep space probes experience signal delays that hinder real-time course corrections. For an object like 3A Atlas moving at high velocity, even a few minutes delay could mean missing the optimal observational window. This requires spacecraft capable of high autonomy, decision-making without Earth-based commands. Observation limitations exacerbate the challenge. The faintness of interstellar comets and their distance during most of the flyby period mean that accurate tracking requires high-precision instruments and continuous monitoring. Any error in early detection magnifies over time, further narrowing the window for a successful intercept. Environmental factors in space, including solar radiation, micrometeoroids, and temperature extremes, impose additional design constraints. Instruments must endure harsh conditions while maintaining calibration to detect subtle signals from the target. This creates further engineering complexity and increases the cost and risk of a potential intercept mission. Even with theoretical propulsion breakthroughs, mission planning requires years of preparation. The logistical challenges of launching a craft capable of high-speed rendezvous with a fleeting interstellar visitor are immense. 3I Atlas serves as a stark reminder that observation from existing orbital platforms is far more practical than direct interception with current technology. Understanding these limits refines expectations. While curiosity drives the imagination toward chasing interstellar visitors, engineering realities and orbital mechanics dictate that for now, the best strategy is careful observation from afar. Mars orbiters, space telescopes, and predictive modeling allow scientists to extract maximum data without attempting the impossible. If speed and distance prevent interception, How can we optimize remote observation and sampling to learn the most from fleeting interstellar travelers like 3I Atlas? Let us take you through the secrets. How post-perihelion heating rewrites the story. As 3I Atlas swings past perihelion, the comet's surface undergoes rapid thermal evolution. Intense solar radiation heats the nucleus, causing sublimation of volatile compounds. CO2 and other ices that were previously frozen solid begin to vaporize, producing a denser, more complex coma. The outgassing rate accelerates, revealing layers that were hidden during its inbound journey. The thermal response of the comet varies by depth and composition. Outer layers, already depleted by prior solar exposure, sublimate first, while deeper strata may retain more pristine materials. As heat penetrates, previously inaccessible water ice and organics can emerge, temporarily altering the CO2:H2O ratio observed earlier. These changes offer a live view into the internal structure of an interstellar object. Chemical evolution is amplified during post-perihelion heating. Molecules trapped in ice can undergo photolytic and thermal reactions as they are released into the coma. The resulting transient species, such as free radicals or short-lived organics, provide an evolving chemical signature. Observers can track these shifts to infer both the original composition and the effects of interstellar aging on the comet's materials. Dust release is equally dynamic. Heating loosens grains embedded in the ice matrix, expanding the dust tail and enhancing the coma's brightness. Fine particles may carry isotopic and organic information, offering Mars orbiters and space telescopes new opportunities to sample material that was previously obscured. Each dust grain becomes a messenger from the comet's internal layers, reshaping our understanding of its formation. Observational timing is critical. The peak of post-perihelion activity often coincides with changing viewing geometries, particularly as 3I Atlas recedes from the Sun. This creates unique challenges for Earth-based telescopes, which must contend with decreasing brightness and increasing distance, while orbiters on Mars or other platforms capture the unfolding transformations from advantageous angles. The coma's visual appearance can change dramatically. Green hues from dicarbon and cyanide may intensify or shift as new layers are exposed. Variations in fluorescence offer clues about molecular excitation, jet activity, and the distribution of volatile compounds. Observing these shifts enhances our ability to correlate visual features with specific chemical processes occurring deep within the comet. Post-perihelion dynamics also influence trajectory subtly. As increased outgassing produces reactive forces, minor changes in orbit may occur, although hyperbolic velocities dominate. Tracking these perturbations refines models of non-gravitational forces on interstellar objects, helping differentiate between natural physics and previously hypothesized anomalies. These processes have broader implications for planetary science. Understanding how heating modifies cometary composition informs models of solar system comets, asteroid interactions, and potential delivery of organics to planets. 3I Atlas acts as a natural laboratory, providing data that extends beyond a single flyby, offering insight into interstellar chemical evolution under solar influence. Data collected during post-perihelion evolution sets the stage for future study. Variations in volatile release, dust density, and molecular excitation inform predictive models for subsequent interstellar visitors. Observing how 3I Atlas responds to heating allows scientists to anticipate chemical and physical changes in similar objects, enhancing preparedness for the next interstellar encounter. If solar heating can unveil hidden layers and new chemistry within 3I Atlas, what secrets lie in wait for the next interstellar visitor, and how will these revelations reshape our understanding of planetary formation and cosmic chemistry? Come along as we uncover the hidden story. What 3I Atlas teaches us about other solar systems. 3I Atlas acts as a messenger from an entirely different planetary system, carrying clues about the formation environments of distant stars. Its unusual CO2-rich composition, combined with an atypical CO2:H2O ratio, provides evidence that chemical diversity in protoplanetary disks can produce bodies drastically different from those found in our own solar system. Each measurement of its coma chemistry offers a glimpse into the conditions of a foreign stellar nursery. The presence of specific organic molecules, such as carbon-bearing compounds and nitrogen-rich species, informs our understanding of chemical pathways beyond the solar system. These molecules suggest that complex chemistry occurs in other protoplanetary disks, potentially enabling the formation of prebiotic materials in regions previously considered inhospitable. Studying 3-bimetal A atlas allows scientists to compare these processes with models derived from solar system comets, as isotopic ratios further illuminate formation environments. Deviations from solar system norms hint at stellar types, disk temperatures, and radiation exposure unique to the object's origin. By combining isotopic data with volatile measurements, researchers can infer the distance from its parent star at which the comet formed and the conditions that preserved its unusual composition over millions of years. Orbital and physical characteristics also teach us about ejection mechanisms in other systems. Hyperbolic trajectories demonstrate how planetesimals can be scattered into interstellar space, offering insight into dynamical histories and planetary architecture in distant systems. 3i Atlas exemplifies how small bodies can survive interstellar travel intact, maintaining signatures of their birth environments. The study of 3i Atlas pushes us to reconsider long-held assumptions about how planetary systems form. Observing even a single interstellar object demonstrates that chemical compositions and dynamical behaviours vary far beyond our own solar system. Analysing it encourages the development of broader models for planet and comet formation, emphasising the wide range of outcomes possible when protoplanetary disks evolve under different conditions of temperature, pressure, and radiation. If one small comet can carry such profound information about distant star systems, what hidden diversity awaits discovery in the next interstellar visitor? And how will these revelations redefine our models of planetary evolution? Let us take you inside the untold truth. The questions that outlive the flyby. The fleeting passage of 3A Atlas leaves more questions than answers, emphasising the transient nature of interstellar exploration. Observations collected during its flyby provide invaluable data, yet they also highlight the limitations inherent in studying objects that traverse our solar system in mere weeks. Scientists are left with an evolving puzzle, piecing together information from dust, light, and spectra to understand a visitor from another star. One enduring question concerns the formation environment of 3 Atlas. Its CO2-rich composition and unusual chemical ratios challenge existing models of protoplanetary disk chemistry. Did it form near a CO2 ice line, or are its peculiarities the product of interstellar processing over millions of years? Untangling these possibilities requires careful comparison with solar system analogues and other interstellar objects. The comet's green coma also raises interpretive questions. The observed fluorescence from dicarbon and cyanide informs us about chemical processes, but variations over time may signal deeper internal layering. How do thermal waves from perihelion expose new materials, and what does this reveal about the physical structure of interstellar comets? Such questions remain partially unanswered until more observations can be compared with predictive models. Observational gaps, such as those created by solar conjunction, further complicate the narrative. Missing data during critical periods forces reliance on extrapolation and simulation, leaving uncertainties in trajectory, outgassing behaviour, and volatile distribution. How can future missions or instruments mitigate these blind spots, and what techniques will best capture transient phenomena in rapidly moving targets? Another area of inquiry involves the broader implications for exoplanetary systems. Interstellar objects like 3i Atlas act as natural probes, delivering clues about chemistry, dust, and organic molecules from distant systems. What do these findings suggest about the potential for prebiotic material seeding in other planetary systems? And how might this influence our understanding of habitability beyond the solar system? The flyby highlights the complex relationship between humanity and the cosmos. Ethical responsibilities, planetary protection, communication strategies, and public fascination converge with scientific objectives. How can we pursue curiosity responsibly, ensuring that discoveries about interstellar visitors advance knowledge without risking contamination or misinterpretation? Every measurement, observation, and model adds to our understanding of interstellar chemistry dynamics and the diversity of planetary systems. Though its visit lasted only weeks, the questions it raises will influence research priorities, observational approaches, and ethical discussions for years to come. What fascinates you most about 3i Atlas? its strange CO2-rich composition, the mysterious green coma, or the possibility that it's seeding Mars with interstellar organics? Share your theories in the comments.